Hey everyone, and welcome to the course on design principles. Get ready to level up your coding skills as we dive into essential concepts like encapsulation, composition over inheritance, and the solid principles. You'll learn how to create maintainable, scalable, and robust software while avoiding common pitfalls. This course is packed with hands-on coding exercises and practical examples to solidify your understanding. Be sure to check out the description for a link to the GitHub repository where you can access all the code we'll be covering. If you're excited to enhance your programming toolkit, don't forget to subscribe for more content. Now, let's get started. Design principles form the foundation of any well-architected software. They guide developers in creating maintainable, scalable, and robust applications while steering clear of common design pitfalls. In this video, we will explore some essential design principles that every developer should incorporate into their programming toolkit. In this example, we define a circle class that exemplifies the principle of encapsulating what varies. The class has an initialization method that sets a private attribute radius, ensuring that this crucial property is controlled. We utilize the @property decorator to create a getter method for the radius, allowing controlled access to the radius value. This encapsulation ensures that users of the class interact with the radius through a defined interface, promoting safety and clarity. Next, we implement a setter method for the radius, which includes validation to prevent the assignment of invalid values, such as negative numbers. This validates the input, reinforcing the integrity of the circle class. When we create an instance of circle, we print the initial radius to demonstrate how the getter works. Subsequently, we change the radius using the setter, which not only modifies the value, but also ensures that any invalid input raises an error, protecting the object's state. This approach showcases how encapsulation can help manage complexity and potential issues in your code effectively. In this section, we examine a practical implementation of the principle of favoring composition over inheritance through a car and engine example. The engine class features a simple method to start the engine, illustrating its responsibilities clearly. In the car class, we establish a composition relationship by creating an instance of the engine class within its constructor. This design allows the car class to leverage the functionality of the engine without the complexities and rigidities associated with inheritance. When the start method of the car is invoked, it first calls the start method of the engine instance, demonstrating collaboration between the two classes. This way, the car class remains decoupled from any specific engine implementation, enabling developers to easily swap out one engine type for another without affecting the car class itself. This flexibility leads to a more robust code base that is easier to maintain and extend, showcasing the advantage of using composition to build scalable and reusable software components. In this segment, we will explore the concept of programming to interfaces through the implementation of abstract base classes in Python. We begin by importing the necessary modules and defining an interface called myInterface. This interface utilizes the abstract method decorator, marking the doSomething method as an abstract method that any class implementing this interface must define. This establishes a contract that ensures any concrete subclass adheres to a specific method signature. Next, we create a class, myClass, which extends myInterface and provides its own implementation of the doSomething method. By encapsulating the functionality within this abstract interface, we can easily switch out myClass with other subclasses in the future without affecting the code that depends on myInterface. Finally, in the main execution block, we instantiate myClass and invoke the doSomething method, passing a parameter. This structure not only enhances flexibility in our code design, but also aids in testing by allowing for mock implementations that adhere to the interface, fostering a more modular and maintainable codebase. The provided code illustrates the principle of loose coupling through the implementation of the message service class, which is designed to interact with different messaging strategies without being tightly coupled to any specific one. In this design, the message service constructor receives a sender object, which could be either an instance of the email sender or the SMS sender class. This flexibility allows the message service to send messages without knowing the details of how the sending is executed. Each sender class defines its own send method, which encapsulates how messages are actually sent. When the send message method is invoked on message service, it simply calls the send method of the sender object, demonstrating how components can communicate through well-defined interfaces. This structure enhances maintainability. If a new messaging method is added, such as a push notification sender, it can be implemented without altering the existing message service class. Additionally, this design simplifies testing, as developers can inject mock senders during unit tests, allowing them to verify the message service behavior independently from the actual sending mechanisms. This adherence to the loose coupling principle provides a robust framework for scalable applications. In summary, these foundational design principles serve as essential guidelines for writing better, more maintainable, and flexible software. Whether you're encapsulating what varies, favoring composition over inheritance, programming to interfaces, or implementing loose coupling, these concepts will significantly improve your code quality and help you avoid many common pitfalls in software development. So grab a pen, take notes, and start applying these principles in your projects. Thank you for watching, and don't forget to subscribe for more insights into clean code practices. Design principles are the backbone of software development, ensuring your code is clean, maintainable, and adaptable to change. In this session, we will explore the core design principles that all developers should know and apply in their projects. So far, we learned that design principles are crucial for creating maintainable and scalable software, guiding developers to avoid common pitfalls. We explored key concepts like encapsulating what varies, favoring composition over inheritance, programming to interfaces, and implementing loose coupling to enhance flexibility and reduce dependencies. Each principle contributes to writing clean, adaptable code, aiding in efficient maintenance and development. Applying these principles will significantly improve code quality and overall project success. Let's examine the initial implementation of our library management system. In this code, we define a library class that is responsible for managing a collection of books. The init method initializes an empty list to hold the books. The addBook method allows us to add a new book to the collection. Additionally, the printBooks method iterates through the list of books and prints their titles to the console. However, this design violates the single responsibility principle, SRP, since the library class manages both the book records and their display logic, leading to potential complications when modifications are needed. The book class encapsulates the book title, ensuring that we have a neat representation of a book object. Following the SRP, we refactor this code by separating the printing functionality into a new class named bookPrinter. This class has a static method called printBooks, which takes a list of books and handles their output. By splitting responsibilities, we enhance code clarity and maintainability, allowing changes in one area without impacting others. Let's delve into an illustration of the open-closed principle using a shape area calculator. Initially, we had a basic shape class that determined the area based on the type of shape provided, like squares and circles. However, this design requires modification each time we want to add a new shape, which violates our principle of extensibility without altering existing code. To improve our design, we define an abstract shape interface that mandates each shape to implement its own area method. This decouples the area calculation from the specific shape types, allowing us to easily add new shapes, like the rectangle, by simply creating a new class without changing the existing implementation. In the revised design, we introduce a calculate_area function that iterates through a list of shapes and invokes their respective area methods, effectively encapsulating the functionality and adhering to OCP. This not only aligns our code with best practices, but also enhances flexibility, making the system robust against future changes. By leveraging abstraction, we foster a clean, maintainable codebase that supports ongoing development efficiently. In our previous example, the library class directly utilized the email service to manage notifications, tightly coupling these two components. This approach violates the dependency inversion principle, as any changes to the email service would necessitate modifications to the library class, thus increasing maintenance challenges. To enhance flexibility, we introduced an abstraction called notification service, allowing the library class to depend on this interface rather than concrete implementations. By doing so, we can seamlessly switch between different notification methods, like SMS or email, without altering the library's core functionality. The email service and a new SMS service are implemented as subclasses of notification service, each defining their notification mechanism. This design not only complies with DIP, but also promotes modularity, making the codebase easier to extend and maintain. When creating an instance of the library, we can pass any specific notification service, demonstrating how easy it is to adapt to different notification needs. This approach improves scalability and encourages adherence to best practices, ensuring our application is robust and maintainable in the long run. In this section, we explore the implementation of the interface segregation principle, ISP, through a notification system designed to handle alerts via different channels such as email and SMS. Initially, both the email notification service and SMS notification service inherit from a general notification service class, which forces them to implement methods they don't use, violating the ISP. To refactor this design, we introduce more focused interfaces, where email service and SMS service are created to handle specific notification types. The email notification service implements only the send email method, while the SMS notification service implements the send SMS method. This change allows each service to have a clear responsibility and eliminates unnecessary method implementations. The result is cleaner, more maintainable code that adheres to the ISP, ensuring that classes are not burdened with methods that are irrelevant to their functionality. By structuring code this way, we promote flexibility and clarity, making it easier to extend our notification system with additional services in the future. Thus, each service remains focused solely on its designated task, enhancing the overall quality of the codebase. In summary, we've explored several core design principles, including the single responsibility principle, the open-closed principle, the dependency inversion principle, and the interface segregation principle. These principles emphasize the importance of structuring code in a way that is maintainable, adaptable, and easy to extend. By adhering to these principles, you can reduce complexity, minimize the risk of bugs, and foster a smoother development experience. As you dive into software development, keep these principles in mind. Implementing them takes practice and commitment, but the rewards, like a cleaner code base and easier maintenance, are well worth the effort. Thanks for joining me today, and I hope you're excited to apply these principles in your own projects. Don't forget to like, subscribe, and share for more insights on mastering clean code practices. In this session, we're diving deep into advanced object-oriented design, focusing on the solid principles that stand as pillars of clean and maintainable code. So far, we learned that design principles are essential for creating maintainable and scalable software, guiding developers to avoid common pitfalls by emphasizing concepts like encapsulation, composition over inheritance, and loose coupling. We discussed the single responsibility principle, SRP, the open-closed principle, OCP, the dependency inversion principle, DIP, and the interface segregation principle, ISP. Now, we will cover the remaining principles, list curve substitution principle, LSB, and the overall importance of applying these principles correctly in advanced object-oriented design. In this section, we implement a class hierarchy to demonstrate the list curve substitution principle. We start with the rectangle class, which includes an initializer to set its width and height, and a method to calculate the area. This basic structure allows us to define rectangles with arbitrary dimensions. Next, we define the square class, which inherits from rectangle. Here, we enforce the square's constraint by passing the same value for both width and height when calling the superclass's initializer. This design mirrors real-world relationships, where a square is indeed a specialized type of rectangle. The printArea function highlights how instances of both classes can be treated interchangeably. It takes a rectangle object as an argument and prints its area, illustrating LSB by accepting both rectangle and square objects seamlessly. When we create a rectangle with specific dimensions and a square with equal sides, we see that both respond correctly to the printArea function without errors. This adherence to LSB emphasizes that subclassing should not disrupt the expected behavior established by the superclass, promoting clean and maintainable code. In this section, we will explore an implementation of the composition over inheritance principle through the concepts of behavior classes for a vehicle. We start with two behavior classes, drive behavior and fly behavior. Each class encapsulates a specific behavior that our vehicles can perform, with drive behavior defining a method to simulate driving, while fly behavior does the same for flying. Next, we define the car and airplane classes. Instead of inheriting from a common vehicle superclass, both classes instantiate the relevant behavior classes in their constructors. The car class uses drive behavior to provide the functionality for driving with its performDrive method, and the airplane class uses fly behavior to enable flying through its performFly method. This approach not only promotes greater flexibility, since we can interchange behaviors or add new ones without disturbing existing code, but also enhances code readability and maintainability. Finally, the examples demonstrate how to create instances of both car and airplane and invoke their specific behaviors, illustrating the practicality of composition in object-oriented design. In this segment, we introduce the push notification service, which highlights the flexibility that solid principles bring to extending functionality in a system. This class inherits from notification service, demonstrating the power of inheritance while keeping the main notification framework intact. The notify method within this class overrides the same method from its parent, allowing us to define specific behavior for sending push notifications. When we create an instance of push notification service, we can call its notify method to send a push notification message to users. This design allows developers to introduce new notification methods without altering existing classes, hence maintaining a clean separation of responsibilities. The print statement within the notify method shows how we provide feedback when a push notification is triggered, reinforcing the simplicity of implementation while adhering to solid principles. Overall, this implementation exemplifies how easy it is to extend existing functionalities by creating new classes that align with established interfaces, ultimately enhancing the maintainability and scalability of the application. In this section, we will examine a unit test designed to validate the behavior of the email notification service class. The test is structured using Python's Unitist framework, which provides a robust way to create and run tests for your code. First, we define a test class, test email notification service, that inherits from Unitist test case. This inheritance gives us access to useful testing methods and assertions. Within this class, we implement the method test_send_email, where we create an instance of the email notification service. Instead of calling the actual send_email method, we use MagicMock to simulate its behavior, allowing us to define our expected return value. This means we can test its functionality without requiring any email service to be operational, making our tests isolated and reliable. Next, we call the mocked send_email method with a test message and check whether the returned response matches our expected output. The assertion ensures that the method behaves as intended when it is invoked. To run the tests, we include a standard unitist invocation, which executes all test methods in the class. This approach underscores how well-structured, solid-compliant code allows for straightforward testing, enhancing the reliability of your software. As we wrap up our exploration of advanced object-oriented design through solid principles, it's crucial to reflect on the entire picture. The solid principles, encompassing SRP, OCP, LSP, DIP, and ISP, provide a framework for developing software that is clean, maintainable, and scalable. When applied correctly, these principles foster an environment where developers can focus on delivering value rather than wrestling with messy code or convoluted design. They empower teams to navigate the complex waters of software development by providing a shared understanding of best practices that can guide decision-making at all levels. Remember, the goal is not simply to adhere to these principles, but to cultivate a mindset that continuously looks for opportunities to apply them in your projects. As the landscape of software engineering evolves, the principles of clean code and object-oriented design will remain foundational. As you embark on your coding journey, apply what you have learned about these principles and take pride in writing code that stands the test of time. With great power comes great responsibility, and by embracing solid principles, you become not just a coder, but a craftsman whose works maintain clarity and elegance in the ever-changing world of software. Thank you for joining me today, and don't forget to practice these concepts in your development work. In the world of software engineering, principles and best practices are the backbone of a robust, maintainable, and efficient code base. Understanding these principles can significantly enhance your ability to construct software that not only functions well, but also evolves gracefully over time. Today, we're diving deep into the solid principles, a set of design guidelines that aim to create more understandable, flexible, and maintainable software. So far, we learned about the importance of solid principles in advanced object-oriented design, which help create clean, maintainable, and scalable software. We discussed principles such as the single responsibility principle, SRP, open-closed principle, OCP, dependency inversion principle, DIP, interface segregation principle, ISP, and list curve substitution principle, LSP. Emphasizing composition over inheritance further enhances flexibility and maintainability in code. Ultimately, adopting these principles fosters a mindset that values clean coding practices and encourages robust development. Now we will talk about what each solid principle entails and how to employ them in your designs. In our exploration of the single responsibility principle, SRP, let's analyze the refactored code which separates concerns effectively. The report class is now solely tasked with generating report content. It takes a string input for its content during initialization and has a method to display that content. By isolating this functionality, we ensure that any future changes to how reports are generated can occur within this class alone, without risking unintended side effects elsewhere. In parallel, we introduce the report saver class, which is dedicated exclusively to saving reports to files. This class requires a report instance upon initialization, showcasing a clear relationship between the two classes, yet adhering to SRP by not mixing responsibilities. The saving function ensures the content is written to a specified file while keeping the report generation logic intact and separate. This design adheres to best practices by enhancing maintainability and ensuring that each class has a singular focus. Following this approach, not only simplifies debugging, but also allows for easier future enhancements, reflecting the core essence of the SRP. In this section, we demonstrate the open-closed principle, OCP, through the implementation of a system for calculating the areas of different geometric shapes. Initially, we create a rectangle class with attributes for width and height, and a function called calculateArea that takes a rectangle instance to compute its area. However, if we wanted to introduce new shapes like circles, we would have to modify this function, violating the OCP. To adhere to this principle, we design an interface called shape using the protocol feature. This interface defines a method area that all shape classes must implement. By doing this, we decouple the area calculation from specific shape implementations. We then redefine the rectangle class to include the area method, and we introduce a new circle class that follows suit, encapsulating its radius and providing its own area method. Finally, we modify the calculateArea function to accept any object adhering to the shape interface, allowing flexibility. This design means that new shapes can be introduced easily without modifying existing code, ensuring our code remains stable and extensible. In this section, we explore the implementation of the list curve substitution principle, LSB, through two different approaches to modeling birds. Initially, we define a base class called bird, which contains a method named fly. A subclass, penguin, inherits from bird, but overrides the fly method to reflect that penguins cannot fly. This design leads to a violation of the LSB because passing a penguin instance to the function makeBirdFly causes unexpected behavior. It fails to meet the expectations set by the base class. To adhere to the LSB, we refactor our classes to create a more functional relationship between the parent and child classes. We redefine the bird class with a more generic move method. Two subclasses, flying bird and flightless bird, are created, each implementing their own movement behavior, either flying or walking. This adjustment allows the makeBirdMove function to operate correctly with any bird type, ensuring that the derived classes can be substituted for their parent class without altering the desired behavior, thus achieving a robust and flexible design aligned with the principles of polymorphism. In this section, we delve into the interface segregation principle, ISP, demonstrated through the use of multiple interfaces for printer functionality. The first class, all-in-one printer, consolidates various functionalities such as printing, scanning, and faxing into a single entity. While this may seem convenient, it forces any implementation that utilizes the all-in-one printer to implement all methods, regardless of necessity. To address this inefficiency, we introduce three specific interfaces: printer, scanner, and fax. Each interface outlines only the methods pertinent to its responsibility, enabling the creation of classes that implement only what they need. For instance, the simple printer class showcases this principle by defining only the printing capability, thereby avoiding unnecessary implementation of scanning and faxing functionalities. This approach not only aligns with the ISB by ensuring that classes are not burdened with unused methods, but also enhances code readability and maintainability. Consequently, each class remains focused on its specific role, simplifying future modifications or extensions, ultimately fostering a cleaner and more efficient codebase. In the following code, we implement the dependency inversion principle through an improved notification system. Initially, the notification class directly instantiated an email class, creating a tight coupling between the two. In the refactored design, we introduce a message sender interface, allowing both the notification class and the email class to depend on this abstraction instead of each other. The message sender interface defines a send method, which any message sending class must implement. This permits flexibility in our architecture. For instance, we can easily introduce alternative message senders like SMS or push notifications that also conform to the message sender interface. the notification class is modified to accept a message sender instance via its constructor, enabling it to call the send method on whatever sender is provided. This approach not only adheres to the dependency inversion principle, but also promotes loose coupling, enhancing maintainability and scalability. Consequently, if any changes are required in the message sending logic, they can be made without affecting the notification class, fostering a more adaptable design overall. In summary, the solid principles of software design are crucial for writing clean, maintainable, and scalable code. By applying these principles, single responsibility, open-closed, list-curve substitution, interface segregation, and dependency inversion, you foster a more robust foundation for your software systems. It encourages better programming practices, minimizes errors, and ensures that modifications and extensions can be made with confidence. So, as you embark on your coding journeys, remember these principles and strive to create software that stands the test of time. The Single Responsibility Principle, SRP, is a fundamental concept in software design. It states that a class should have one, and only one, reason to change, meaning it should only have one responsibility or functionality. Today, we're going to dive deep into the nuances of SRP, why it matters, and how you can start applying it in your software projects. So far, we learned about the solid principles in software engineering, emphasizing the importance of creating clean, maintainable, and scalable code. We discussed the single responsibility principle, open-closed principle, list-curve substitution principle, interface segregation principle, and dependency inversion principle. Now, we will cover practical applications of the single responsibility principle. The initial implementation, which features the report generator class, is a common example of violating the single responsibility principle. This class is burdened with multiple tasks. It generates the report and handles the saving process. By combining these functions, any changes to the report saving mechanism would necessitate modifications within the same class, leading to tight coupling and reduced maintainability. In contrast, the refactored version introduces two distinct classes, report and report saver. The report class focuses solely on holding the report's data and displaying its contents, ensuring clarity in its role. The report saver class, on the other hand, is dedicated to managing how the report is saved, either as a text file or a PDF format. This meticulous separation of responsibilities enables easier adjustments and enhancements, allowing developers to modify file-saving methods independently of report generation. Consequently, the code becomes more organized and modular, facilitating maintenance and future development while adhering to the principles of clean software design. In this section, we explore the application of the single responsibility principle through a refactored design for calculating and displaying the area of different shapes. We begin by defining specific classes for each shape, such as rectangle and circle. Each of these classes has its own constructor to initialize the necessary dimensions and a method to calculate the area. This separation ensures that adding new shapes in the future won't require modifications to existing classes, enhancing maintainability. Next, we introduce the area calculator class, which contains a static method to compute the area of any shape passed to it. This class centralizes area calculation functionality without being tied to specific shapes, reinforcing the principle of distinct responsibilities. Finally, we introduce the area display class, which handles the task of outputting the area result. This clear division of responsibilities results in code that is easier to understand, test, and modify, allowing developers to work on each component without impacting others, thereby adhering to the foundational principles of clean software design. In this section, we focus on refactoring a user authentication system to adhere to the single responsibility principle, SRP. Initially, we had a user manager class that handled both user management and authentication. This design causes problems in maintainability and scalability, as changes to authentication logic would affect the entire class. To improve this, we introduced a user class dedicated to holding user data like username and password. The user manager class is now solely responsible for managing the user list, simplifying user addition. We then created an authenticator class tasked exclusively with the authentication process. This clear separation of concerns allows changes to authentication methods without altering user management logic. Additionally, this refactoring enhances code readability and testing. Each class is focused on a single responsibility, making it easier for developers to understand and work on individual components. Consequently, if we need to implement new authentication methods or user management features in the future, the impact on the overall system will be minimal, ensuring a more robust design. Finally, let's address the broader implications of the single responsibility principle for your software architecture. By adhering to this principle, you're not just making your code cleaner and more maintainable, you're also facilitating teamwork. When multiple developers work on the same project, a clean separation of concerns helps everyone understand how different parts fit together, reducing the chance of conflict and confusion. Think about a large-scale application where different teams might handle various features. If each feature's classes strictly follow the SRP, Team A can work on their functionality without hindering Team B's environment. If the architecture is messy and responsibilities are mixed, it may lead to unforeseen issues when one team alters a component that another team relies on. Additionally, unit testing becomes significantly easier when you adhere to SRP. By ensuring each class has only one responsibility, you can write focused tests for that behavior, simplifying both setting up the test environment and debugging when things go wrong. Less coupling means more robustness in your tests, and you'll find that you can pinpoint problems faster. To summarize our journey through the single responsibility principle, we explored its importance and how it manifests in practice through various examples. We demonstrated how a tangled web of responsibilities can morph into a beautifully modular structure, enhancing readability, maintainability, and testability. Adopting the single responsibility principle is not just an academic exercise, it's a practical approach to building software that stands the test of time. So, as you embark on your coding adventures, keep the SRP in mind. It's not merely an acronym to remember, but a guiding philosophy that can dramatically improve your software design. Embrace it, and you'll find your code is more organized, easier to manage, and a joy to work with. Happy coding! The open-closed principle, OCP, is another fundamental principle in software design. Understanding and applying OCP can significantly enhance your software architecture, making it more resilient to change and easier to extend. So far, we learned about the single responsibility principle, SRP, in software design, emphasizing that a class should have only one responsibility. We explored various examples demonstrating the importance of separating concerns for better code maintainability and readability. Additionally, we discussed how SRP enhances collaboration in team environments and simplifies unit testing. Ultimately, SRP serves as a guiding philosophy for creating robust and scalable software solutions. Now, we will dive into the open-closed principle, explore its significance, and understand how we can implement it in our coding practices. In this section, we define a shipping cost calculator class responsible for calculating shipping costs based on various methods. The calculate cost method takes two parameters: method, which identifies the shipping option like standard or express, and weight, which represents the weight of the package. Inside the method, we utilize conditional statements to return the cost based on the selected shipping method: $1, 0 per kilogram for standard shipping, and $2 for express shipping. If an unknown method is provided, the function raises a value error, ensuring that any incorrect usage is clearly flagged. While this class functions adequately for standard and express methods, it illustrates a limitation when trying to extend functionality, such as adding international shipping. To comply with the open-closed principle, we would need to modify this existing code, which poses risks of introducing errors. Thus, we begin to recognize the need for a more flexible design that adheres to this principle, enabling future extensions without altering the existing implementation. This sets the stage for a refactoring approach that embraces more scalable and maintainable coding practices. In this code, we implement the open-closed principle by creating a flexible and extensible shipping cost calculation system. At the heart of this design is the shipping method base class, which includes an abstract method, calculate cost. This method is intentionally not implemented, requiring subclasses to provide their own specific calculation logic. We then define three shipping method classes: standard shipping, express shipping, and international shipping, where each class overrides the calculate cost method to calculate shipping costs based on different rates. The shipping cost calculator class serves as a client that utilizes these shipping methods. It takes an instance of shipping method and a weight parameter to invoke the appropriate shipping method's calculation, enabling easy extension by adding new shipping methods without modifying existing code. For instance, if a new shipping option arises, such as next-day shipping, one simply needs to create a new class that inherits from shipping method. This structure exemplifies how we adhere to the principle of being open for extension, yet closed for modification, promoting maintainability and scalability in our software design. In this section, we explore a payment processing system designed to adhere to the open-closed principle by utilizing interfaces and polymorphism. Initially, the payment processor class manages credit card payments with a method that checks the payment type and processes accordingly. While this approach works for a single payment method, it is fragile. Adding new payment types would require modifying the car class, which could introduce bugs. To address this, we introduce a payment method interface that standardizes the payment processing structure. Each specific payment method, such as credit card payment and PayPal payment, inherits from this interface and implements the process payment method. This allows for easy extension of the system. Should you want to add a new payment service, you can simply create a new class that implements the payment method interface without altering the existing payment processor. Lastly, the payment processor class is updated to accept any payment method instance, allowing it to process payments dynamically based on the specific method used, thus enhancing the system's flexibility and maintainability while minimizing the risk of bugs. In our implementation of the strategy pattern for calculating shipping costs, we start by defining the base class, shipping cost strategy, which establishes a contract for all shipping strategies by including an abstract method, calculate cost. This method will be overridden by subclasses to define specific cost calculations based on different shipping methods. We then create two concrete classes, standard shipping cost and express shipping cost, each implementing the calculate cost method to provide the respective cost calculations based on the weight of the package. Next, we introduce the shipping cost calculator class, which accepts a shipping cost strategy upon initialization. This design allows us to switch between different shipping strategies seamlessly. By calling the calculate method and passing the weight, the calculator delegates the cost calculation to the current strategy. This modular approach exemplifies the open-closed principle, as we can introduce new shipping methods by simply creating additional subclasses of shipping cost strategy without modifying any existing code in the calculator. This enhances maintainability and adaptability, showcasing the power of design patterns in software development. In this section, we will look at a unit test for our payment processing system, which demonstrates the implementation of the open-closed principle through individual payment methods. The test is structured using the unitist framework and consists of two main methods, each designed to validate the functionality of a specific payment method. The first test method, test credit card payment, creates an instance of the payment processor and a credit card payment object, simulating a payment of 100 units. It calls the process payment method of the processor and then checks if the returned result matches the expected string, confirming that the payment was processed correctly. Similarly, the test PayPal payment method performs a test for the newly integrated PayPal payment class, attempting to process a payment of 200 units. Again, the test verifies that the output aligns with the expected response. This separation of tests for each payment class showcases the benefits of adhering to the open-closed principle, as each payment method can be tested independently, allowing for better clarity and easier troubleshooting in case of issues. Thus, the design promotes reliability and enhances the overall testability of the code. As we wrap up, it's essential to remember that the open-closed principle, while powerful, is one of several core principles that a strong software architect should embrace. It's important not to fall into the trap of applying it dogmatically. Instead, leverage OCP judiciously, balancing between simplicity and the need for extensibility. To summarize, we've explored the open-closed principle in depth, uncovering its implications for software design. We've seen how it allows for the extension of capabilities without modifying existing code, enhancing maintainability and reducing errors. Through practical examples, we illustrated how to implement OCP with inheritance, composition, and the strategy pattern. As you continue your journey in software development, consider the open-closed principle as a guiding light for creating more organized, scalable, and resilient code. The principles we've discussed today are not merely theoretical. They shape the foundations of robust software design and can lead you to higher quality products in the long run. So stay curious, keep coding, and embrace these principles to elevate your skills as a software developer. Happy coding! Design patterns are reusable programming solutions that have been used in various real-world contexts and have proved to produce expected results. In today's lesson, we will explore creational design patterns, a category that focuses specifically on how objects are created in software engineering. So far, we learned about the open-closed principle OCP and the single responsibility principle SRP, which emphasize maintainability and clean code. Now, we will dive into the specific methods of object creation and the benefits they bring to our software projects. In this segment of our tutorial, we illustrate the factory method design pattern through a practical example involving shapes. We begin by defining an abstract shape class that features a draw method, which is expected to be implemented by any subclass. This abstraction establishes a uniform interface for different shape types. Here, we've created two subclasses, circle and square, each providing its own implementation of the draw method, demonstrating polymorphism. Next, we introduce the shape factory, which employs a static method called getShape. This factory centralizes the object creation process by taking a shape type parameter and returning an instance of the respective shape class without the client needing to know about the specific classes involved. This decoupling enhances maintainability and scalability, as changes can be made to the shape implementations or the factory logic without impacting the client code. Finally, our client code demonstrates a straightforward usage of the factory method by requesting a circle shape from the factory and invoking its draw method to output the corresponding drawing action. This showcases the ease and flexibility afforded by the factory method pattern in object creation. In this section, we explore the abstract factory pattern and evolution of the factory method. The code begins with a button class that declares a paint method, which is meant to be overridden by its subclasses. We have two concrete implementations, Windows button and Mac OS button, each providing a unique implementation of the paint method, which returns a string indicating the specific platform's button rendering. The GUI factory is defined as an abstract factory with the createButton method that must be implemented by concrete factories. The Windows factory and Mac OS factory classes extend GUI factory, each implementing the createButton method to return their respective button instances. This structure encapsulates the creation of button objects specific to the platform, adhering to the principles of polymorphism. The client code, represented by the getUI function, takes a GUI factory instance and calls its createButton method to generate a button. The button's paint method is called to render the button, demonstrating how easily the UI can switch styles without altering the client code, embodying the flexibility and extensibility offered by the abstract factory pattern. In the builder pattern, we create a structure that allows for step-by-step construction of a complex object, which is particularly useful for an entity with optional configurations, such as a pizza. The pizza class serves as the main object, initialized with an empty list of toppings. It provides a method to add different toppings and a string representation for easy display of the current toppings. To facilitate the customizable creation of the pizza, we employ the PizzaBuilder class. This builder initializes a pizza object and includes methods for adding toppings incrementally, such as cheese, pepperoni, and olives. Each method in the PizzaBuilder is designed to return self, allowing for method chaining. This means you can call multiple topping methods in a single, fluid statement. Finally, the build method finalizes the construction by returning the complete pizza object. In the client code, we showcase how to use this builder to create a personalized pizza by chaining the topping methods, ultimately enhancing readability and maintainability by clearly illustrating the process of constructing complex objects. In this section, we will delve into the implementation of the prototype pattern using a website class. The website class serves as a data holder for website attributes, specifically the name and domain. The class includes a string representation method, allowing instances to be easily printed and displayed, which can be helpful for debugging. Next, we introduce the prototype class, which manages a registry of prototype objects. This class has methods to register new prototypes and to clone existing ones. The register method allows us to add prototypes to the registry by associating a name with a website instance. This is crucial for enabling easy access and reuse of prototypes when needed. When it comes to cloning, the clone method creates a copy of an existing prototype using copy, deepcopy, which ensures that modifications to the new instance do not affect the original. Any additional attributes can be set during cloning through keyword arguments. In practice, we demonstrate this by registering a website instance and then cloning it with new values, allowing for efficient object creation without the overhead of reinitialization. This approach highlights the performance advantages of the prototype pattern in scenarios with resource-intensive object initialization. In this section, we explore the singleton pattern, which ensures that a class has only one instance and provides a global point of access to it. The implementation begins with the singleton meta class, which overrides the call method to control instance creation. When a class using this meta class is called to create an instance, it checks whether an instance of the class already exists stored in the instances dictionary. If not, it creates a new instance and stores it. Otherwise, it returns the existing instance. This mechanism guarantees that any call to instantiate the class results in the same object being returned, thus enforcing the singleton property. Next, we define the logger class with singleton meta as its meta class, indicating that logger will operate as a singleton. The log method allows logging messages, reinforcing the utility of having a single logger throughout the application for consistency. The client code demonstrates this by creating two logger instances. Despite two instantiations, the expression checking if logger1 and logger2 are the same object returns true, indicating the singleton behavior. This example effectively illustrates how the singleton pattern can manage shared, resources conveniently in software applications. In conclusion, we have explored various creational design patterns: the factory method, abstract factory, builder, prototype, and singleton. These patterns provide differing solutions for object creation, helping us tackle challenges related to complexity, flexibility, and resource management. Knowing when and how to utilize these patterns will significantly enhance your coding practice and lead to more robust, maintainable software. As we move forward, we will continue our exploration of design patterns, specifically transitioning into structural design patterns in the next session. Keep practicing the patterns we've covered, as they are vital tools in your software development toolkit. In today's session, we'll delve into two key design patterns widely used in software engineering: the factory method and the abstract factory pattern. These patterns are essential for managing object creation in a flexible and scalable way. So far, we have learned about creational design patterns, emphasizing effective object creation and maintainability. These patterns help developers efficiently create complex objects while promoting scalability and flexibility. Now, we will explore the factory method and abstract factory patterns, examining their differences and use cases, along with practical coding examples. In this implementation of the factory method pattern, we start by defining a shape class that includes a draw method. This method is meant to be overridden by any subclass, ensuring that each shape can implement its own drawing logic. We then create two subclasses, circle and square, which provide their specific implementations of the draw method, returning distinct strings that represent the shapes they draw. Next, we introduce the shape factory class, which contains a static method called getShape. This method takes a shape type as input and determines the appropriate shape to instantiate based on that input. If the type is circle, it creates an instance of the circle class. If the type is square, it creates an instance of the square class. This design allows the client code to create shapes without needing to know the specific classes involved, thus enhancing maintainability and promoting decoupling in the code structure. Finally, a simple client code snippet demonstrates how to utilize the factory to create a circle and call its draw method, showcasing the clean instantiation process. In this section, we explore the abstract factory pattern implemented in Python, which allows for creating families of related objects. We start by defining an abstract button interface that enforces the implementation of a paint method in its subclasses. The Windows button and Mac OS button classes provide specific implementations for rendering buttons on their respective platforms, ensuring that each adheres to the expected interface while differing in behavior. Next, the GUI factory serves as the abstract factory, specifying a method for creating buttons without detailing the concrete classes. Two concrete factories, Windows factory and Mac OS factory, extend GUI factory to instantiate the appropriate button for each operating system. This encapsulation enables easier modifications and enhancements in the future. In the client code, the getUI function takes a factory as an argument, utilizes it to create a button, and returns the rendered output by invoking the paint method. This structure decouples the client from the specific button implementations, allowing for flexibility in switching between different UI elements based on the platform. As demonstrated, using factories streamlines UI creation and promotes code maintainability. In this section, we expand on the abstract factory pattern by introducing a new component, text fields. The text field class serves as the base for creating platform-specific text fields, establishing a consistent interface with the render method, which needs to be implemented by subclasses. We then create two concrete classes, Windows text field and Mac OS text field, each overriding the render method to provide platform-specific behavior for rendering text fields. This modular approach allows us to easily add new UI elements without changing the existing hierarchy. The GUI factory class has been updated to include a new method, createTextField, along with the existing create button. Each concrete factory, Windows factory, and Mac OS factory implements both methods, producing the respective button and text field instances for the targeted operating system. In the client code, the getUI function demonstrates how to utilize the factory to create both a button and a text field, showcasing the seamless integration of multiple components through a unified interface. This structure not only promotes code maintainability, but also allows for easy expansion as new UI elements are required across different platforms. Let's summarize the main benefits of using the factory method and abstract factory patterns. Both patterns promote code maintainability by enforcing a clear separation of concerns between the client code and object creation logic. They enable developers to introduce new products without changing existing code, following the open-closed principle. Moreover, they provide a unified interface for object creation, allowing for more streamlined testing and implementation. Beyond the benefits of code maintainability and flexibility, these patterns also aid in managing complexity. When building large-scale applications, having a clear structure for instantiating products can significantly simplify your codebase. It reduces dependencies on concrete classes and allows for the introduction of new products with minimal disruption. Understanding when to use these patterns is key to leveraging their power. The factory method is great for scenarios where you want to delegate the responsibility of creating objects without dictating which concrete class should be instantiated. It's your go-to option when you need a simple and clean mechanism for generating instances while maintaining the option for subclasses to change the instantiation logic. On the other hand, the abstract factory is best suited for applications that require a suite of related objects. If you find yourself needing to create groups of interrelated products, the abstract factory is your friend. It encapsulates the creation logic, allowing your code to remain flexible as you introduce new product families or alter existing ones. To conclude, exploring the factory method and abstract factory patterns unlocks a powerful approach to object creation in software design. These creational patterns allow developers to manage complexity, enhance maintainability, and foster scalability in their applications. By understanding and applying these patterns effectively, you elevate the quality of your software design and prepare yourself to tackle more complex scenarios with confidence. So, in our next session, we'll transition into structural design patterns, where we will explore patterns that deal with the composition of classes and objects. Keep practicing these creational design patterns, and remember, a well-structured code base is always a joy to work with. In today's lesson, we are diving deep into the builder pattern, a crucial design pattern that streamlines the process of constructing complex objects step by step. This pattern is tremendously beneficial when the object to be created is composed of multiple parts, or when you want to create different representations of the same type of object. So far, we've covered the factory method and abstract factory design patterns, which are essential for managing object creation in a flexible and maintainable way. We explored how the factory method provides an interface for creating objects while allowing subclasses to determine the specific class to instantiate. Additionally, we discussed the abstract factory pattern that facilitates the creation of families of related objects without specifying their concrete classes. Both patterns promote code maintainability, scalability, and complexity management in software design. Now, we will shift gears to focus on the builder pattern and its numerous applications. In this example, we implement the builder pattern through the construction of a house object. The house class serves as a blueprint for our house, encapsulating essential features such as walls, a roof, windows, and doors. Its SDR method is overridden to provide a readable string representation of the house, displaying its components clearly. The house builder class implements the actual building process. Upon initialization, it creates an instance of a house. Each method in the builder, such as add walls, add roof, add windows, and add doors, allows the client to specify the components of the house step by step. Importantly, each method returns the builder itself, enabling a fluent interface through method chaining, which enhances readability. The client code demonstrates how to use the house builder to construct a house, specifying each component in sequence and ultimately calling the build method to finalize the construction. This clean process allows for flexibility and clarity, showcasing how the builder pattern effectively simplifies the construction of complex objects by abstracting the details into separate builder classes. In this implementation of the builder pattern for vehicle construction, we first define a vehicle class that encapsulates common attributes such as type, engine, color, and wheels. This class includes a string representation method, which provides a clear output of the vehicle's information when printed. Next, we create the vehicle builder class, designed to facilitate the construction of different vehicle types. The builder is initialized with a specific vehicle type and provides methods to set features like engine, color, and wheels incrementally. Each method returns the builder instance itself, allowing for method chaining, which enhances the readability and fluency of the construction process. In the client code, we demonstrate how to build a car and a truck using the vehicle builder. For each vehicle type, we specify its attributes by invoking the relevant builder methods before calling build to create the final vehicle object. This method returns an instance of the vehicle class, showcasing one of the key strengths of the builder pattern, the ability to create different representations of a complex object while maintaining a simple and consistent interface for the user. In this section, we enhance the builder pattern implementation to support immutability in our vehicle creation process. The immutable vehicle class is designed to store vehicle attributes such as type, engine, color, and wheels, but once an instance is created, these attributes cannot be altered, ensuring the object's immutability. This is achieved by using private attributes and defining properties for each attribute, thereby allowing controlled access but no modifications after the object is constructed. Complementing this, the immutable vehicle builder class facilitates the step-by-step setup of these attributes before creating an immutable vehicle instance. Each method in the builder, such as setEngine, setColor, and setWheels, allows you to specify an attribute while returning the builder instance for further configuration. Once all desired attributes are set, invoking the build method constructs the immutable vehicle. This structured approach not only maintains clarity and separation of concerns, but also proves particularly useful in multi-threaded environments where consistent object states are critical. The flexibility of the builder pattern allows easy integration of immutability while continuing to benefit from a clear and organized creation process. In this example, we delve into the creation of user interface components using the builder pattern, showcasing its ability to manage complexity effectively. The UI component class serves as a blueprint for our UI elements, encapsulating their type and properties. Through the setProperty method, we can dynamically assign various attributes, such as color or size, to these components. This flexibility ensures that each UI element can be customized without altering its fundamental structure. The UI Builder class acts as the orchestrator of our UI construction process. It maintains a list of components and provides an Add Component method to facilitate their integration into the layout. When a component is added, it is instantiated and appended to the builder's collection. The build method finalizes the process by returning the complete list of components that have been constructed. This approach exemplifies how the builder pattern enhances code organization and readability, making it easier to accommodate different UI configurations by simply changing the component types or their properties. As you can see, incorporating this pattern not only streamlines the creation process, but also fosters clean and maintainable code in user interface designs. Ultimately, the builder pattern brings significant value to software design. It enhances maintainability and readability, particularly for complex objects with multiple components or configurations. The pattern also enforces a clear structure, separating the construction logic from the representation, leading to cleaner and more understandable code. One last tip I'll leave you with is that while the builder pattern is powerful, it's essential to consider its application context carefully. It shines when dealing with complex object creation, but can lead to unnecessary overhead if a simple instantiation would suffice. Therefore, always analyze the problem at hand and assess whether using the builder pattern enhances clarity and structure. In conclusion, the builder pattern stands as a testament to thoughtful design in software engineering. By breaking down the construction process into manageable steps, it allows developers to create complex objects with ease, flexibility, and clarity. Whether it's for creating a house, a vehicle, or even a user interface, the builder pattern enhances your code's maintainability, scalability, and comprehensibility. In our next session, we will explore another fascinating design pattern that can elevate your coding practices even further. Until then, keep practicing and integrate the builder pattern into your projects, and you'll find your object creation workflows feeling more organized and powerful. Structural patterns are a vital aspect of software design, providing elegant solutions to common design challenges we encounter while developing applications. These patterns help us compose objects and classes into larger structures in a way that enhances functionality and promotes code reusability while maintaining clean interfaces. So far, we've learned about the builder pattern, which facilitates the step-by-step construction of complex objects. It allows us to break down the construction process into manageable parts through specialized builder classes. This pattern enhances maintainability and readability, promotes immutability, and encourages clean code structures. Now, we will dive into another category of design patterns: structural patterns. In this lesson, we'll focus on how these patterns can aid us in organizing and optimizing our code. In this example of the adapter pattern, we implement a mechanism to enable interaction between an old system and a new one that uses different methods. The old system class has a method called existingMethod, which serves to simulate the old interface. When called, it returns a simple string indicating that data is being fetched from the old system. Contrastingly, the new system class introduces a different method, newMethod, which returns a string representing data from the new system. To bridge the gap between these two incompatible systems, we introduce the adapter class. This class takes an instance of new system upon initialization and implements the existing method. When this method is invoked on the adapter, it calls the new method of the new system, effectively transforming the request from the old system into one that the new system can understand. Finally, in the usage section, we create instances of old system and new system, along with the adapter, demonstrating how the old interface can now interact seamlessly with the new component through the adapter, ensuring that legacy systems can still operate effectively without modification. In this section, we delve into the decorator pattern with a practical example demonstrating how to extend function behavior dynamically. We start with a simple function, which simply returns a string indicating its basic functionality. By introducing the logger decorator, we create a wrapper function that enhances simple function by adding logging features without altering its core implementation. The logger decorator takes a function as an argument and defines an inner function called wrapper. This wrapper executes the original function while also providing additional logging before and after its execution. Specifically, it prints a message when the function is called and another message once the function completes, showcasing the decorator's ability to seamlessly add functionality around the existing code. Finally, we bind the decorator to simple function, generating decorated function, which retains the original functionality but is now equipped with logging. This pattern exemplifies how decorators can enhance, modify, or add responsibilities to functions elegantly, promoting cleaner and more maintainable code structures. In this section, we explore the implementation of the bridge pattern, which separates an abstraction from its implementation to enhance flexibility. At the core of our code is the remote class, which defines an interface with an operate method. This method is intended to be overridden by specific remote types. We then define two concrete implementations, TV and radio. Each implements the operate method, where TV provides a message indicating that it is on, while radio indicates that it's playing music. This approach allows both types to evolve independently, demonstrating the key benefit of the bridge pattern. The device class acts as a bridge, holding a reference to a remote type, allowing it to delegate operations to the specific remote instance it contains. In the usage example, we create instances of both TV and radio, wrapping them in device objects. As we call the operate device method on these devices, they effectively communicate with their respective remote types, showcasing how the pattern enables the independent variation of abstractions and implementations. The facade pattern provides a simplified interface to a complex system, making it easier for users to interact with it. In our example, we have two classes, CPU and computer. The CPU class encapsulates the intricate operations needed to start up a CPU, including methods to freeze, jump to a specified position, and execute commands. Each of these operations represents a low-level detail of how a computer works, which can be difficult for end users to understand or interact with directly. On the other hand, the computer class acts as a facade that abstracts these complexities. It initializes an instance of CPU and offers a simplified method called start. When users call this method, they do not need to worry about the underlying procedures. They simply invoke start, which handles the necessary steps in the correct order, freezing the CPU, jumping to a specific execution position, and executing commands. This design promotes an easier user experience by hiding the complexities of the underlying system while still enabling functionality, illustrating how the facade pattern can make working with complex systems streamlined and user-friendly. In this section, we implement the flyweight pattern, which focuses on optimizing memory usage by sharing common states among multiple objects. The main component is the flyweight class, which encapsulates the intrinsic state that can be shared across instances. It contains an operation method that takes an extrinsic state as a parameter, demonstrating how different contexts can utilize the same intrinsic data. Complementing the flyweight class is the flyweight factory, responsible for managing the creation and reuse of flyweight objects. This factory maintains a dictionary of existing flyweights, ensuring that if a requested intrinsic state already exists, it returns the same instance instead of creating a new one. This reuse mechanism is crucial for maintaining memory efficiency in applications dealing with numerous objects, particularly in scenarios like graphics rendering, where many similar objects may display varying characteristics. Finally, the usage section illustrates how to create a flyweight factory, instance, and retrieve flyweight objects sharing the same intrinsic state. The subsequent calls to the operation method of different flyweight instances demonstrate how the same intrinsic state can work with different extrinsic states, showcasing the flexibility and efficiency of the flyweight pattern. In this section, we will explore the implementation of the proxy pattern, which serves as a placeholder for another object to manage access to it. The real subject class represents the primary object with a method called request, which returns a string indicating that it is handling a request. To introduce the proxy functionality, we define the proxy class, which takes an instance of real subject during its initialization. The proxy class then overrides the request method, adding an additional feature, logging. Before delegating the request to the real subject, the proxy prints a log statement that indicates the action is occurring. This structure allows the proxy to enhance the behavior of the original object without modifying its code. When using the proxy, an instance of real subject is created, and then a proxy instance is initiated with the real subject as an argument. When the request method is called on the proxy, it executes the logging operation, followed by the invocation of the request from the real subject. This demonstrates how the proxy pattern can be effectively leveraged to introduce extra functionalities, such as logging, while preserving the integrity of the original object's operations. Through these structural patterns, you can enhance how your code interacts and organizes itself. Each pattern has its unique use cases, strengths, and whatever challenges you face in your programming journey, there's likely a structural pattern that offers a solution. By employing the right patterns, your code not only becomes more efficient, but also more readable and maintainable. As we move forward, we will delve into behavioral design patterns, focusing on how objects interact and communicate with one another. Keeping these structural patterns as a foundation will serve you well in understanding the complexities of behavioral patterns. Happy coding! Let's examine a practical implementation of the adapter pattern, which allows integration between incompatible systems. In our example, we have an old system class that offers a method called legacy method, which provides data from the old infrastructure. Conversely, the new system class boasts its own method called new method, producing data using a different approach. To bridge the gap between these two systems, we introduce an adapter class. This class takes an instance of new system as an argument during its initialization. What's crucial here is how the adapter class implements the legacy method. Instead of maintaining the old architecture, it calls the new method from the new system instance. When we create instances of both old system and new system and utilize the adapter, it allows us to seamlessly call legacy method, which in turn executes the new method. This encapsulates the adaptability of the adapter pattern, making it a powerful tool for enabling communication between different components without modifying existing code directly. In this section, we delve into the decorator pattern, which elegantly enhances existing functions with added functionality. The implementation begins with simple function, a straightforward function that simply returns a string message. To augment its behavior, we define logodecorator, which takes a function as an argument. Inside this decorator, we create a nested function called wrapper. This wrapper function is where the magic happens. It first prints a message indicating that the function is about to be called, then invokes the original function, and finally, prints another message once the function execution is completed. The crucial part is that wrapper does not alter simple function, but instead wraps around it, thereby enhancing its functionality without modifying its structure. To apply this decorator, we create decorated function, which is now a decorated version of simple function. When calling decorated function, we actually execute the wrapper, which adds the logging behavior each time the original function is invoked. This approach exemplifies how the decorator pattern promotes flexibility by dynamically adding responsibilities to objects while keeping the core behaviors intact. In this section, we illustrate the bridge pattern through a simple example involving a remote control system. Here, we define an abstract class called remote, which declares a method operate that must be implemented by any subclass. This abstraction allows for the decoupling of the remote control interface from its specific implementations. We then create two concrete classes, TV and radio, both of which extend the remote class and provide their own specific implementations of the operate method. The TV class returns a message indicating that the TV is now on, while the radio class signifies that the radio is playing music. This ensures that we can add different devices easily in the future by extending the remote class. Next, we introduce the device class, which serves as a user interface for interacting with the various types of remotes. It takes an instance of remote in its constructor and has a method operate device that calls the operate method on the appropriate remote. This design allows us to create instances of device for both the TV and the radio, demonstrating how the bridge pattern enables flexibility and extensibility within our code. In this segment, we illustrate the facade pattern through a concrete example involving a simplified interaction with a computer's CPU. Here, we define a CPU class that encapsulates the complex functions associated with a computer's processing unit. This class provides three methods: freeze, which simulates pausing the CPU, jump, which directs the CPU to a certain memory position, and execute, which represents executing commands. To enable users to interact with these functionalities without delving into the complexities of each method, we create a computer class that acts as a facade. The computer class initializes an instance of CPU and exposes a single method called start. When users call this start method, it triggers the sequence of operations in the CPU, freezing it, jumping to a specified position, and executing commands, all in one streamlined process. This abstraction serves to simplify the user's interaction, masking the intricate details behind a single, easy-to-use interface, effectively illustrating how the facade pattern enhances usability in complex systems. The flyweight pattern is designed to optimize memory usage by sharing objects that have similar data. In this implementation, we define a flyweight class that encapsulates an intrinsic state, which remains constant across shared instances. The operation method takes an extrinsic state, providing flexibility while maintaining the efficiency of stored shared states. The flyweight factory then plays a crucial role in managing these shared objects. It contains a dictionary to store instances of flyweight objects by their intrinsic state. When a request for a flyweight is made, the factory checks whether an object with the requested intrinsic state already exists. If it does not, a new flyweight is created and added to the dictionary. Otherwise, the existing instance is returned. This approach ensures that memory is conserved, as multiple requests for the same intrinsic state point to a single object. Finally, in the usage section, we demonstrate how the flyweight factory and its getFlyweight method are utilized. By creating two flyweight instances with the same intrinsic state, we illustrate how the pattern promotes memory efficiency while maintaining distinct extrinsic states, showcasing its effectiveness in scenarios where object creation can be extensive. In this section, we implement the proxy pattern, which acts as a mediator between the client and the real object, allowing us to add additional functionality such as logging. We start with the real subject class, which contains the call functionality we intend to control access to. In this case, it has a simple method called request that returns a message indicating it is handling a request. Next, we introduce the proxy class. This class holds a reference to a real subject instance, which it utilizes to forward requests while adding its own layer of behavior. Before calling the request method on the real subject, the proxy class executes a logging action to indicate that a request is about to be processed. This illustrates how the proxy can be used to add pre-processing tasks without altering the original object's code. Finally, we showcase how to use these classes together. By creating an instance of real subject and then wrapping it with the proxy, we can call the request method on the proxy object. The output demonstrates the logging functionality before revealing the response from the real subject, effectively illustrating the proxy pattern's role in controlling access and enhancing functionality. Through these various structural patterns, we have a toolkit for solving a multitude of challenges in software design. Each pattern not only helps organize and optimize our code, but also encourages a clearer methodology for handling complex interactions among objects. They enhance our understanding of object-oriented design by promoting code reuse, increased flexibility, and cleaner structural organization. As we transition into exploring behavioral design patterns, we build upon these concepts, enhancing our ability to understand how objects communicate and interact efficiently. Remember, mastering these patterns not only makes you a better programmer, but opens up new pathways for innovative solutions in software development. Happy coding! In this session, we'll dive deep into implementation examples and use cases related to structural design patterns in programming. Our goal is to take the abstract concepts we've learned and ground them in real-world applications to enhance your understanding. So far, we learned about various structural design patterns that enhance code organization and efficiency, such as the adapter, decorator, bridge, facade, flyweight, and proxy patterns. Each pattern addresses common design challenges, improving maintainability, readability, and interactions between objects. We also discussed how these patterns provide solutions for integrating incompatible systems, adding functionalities dynamically, and simplifying complex interfaces. Next, we will explore practical implementation examples and use cases to bring these patterns to life. In this section, we implement the adapter pattern to unify interactions with various payment gateways. We begin with the definition of a payment processor abstract class, which establishes a contract for payment operations by defining a pay method. This class is pivotal as it establishes a common interface that all payment adapters will adhere to, promoting code consistency. Next, we create two concrete classes, PayPal and Stripe. Each class encapsulates the specifics of processing payments through their respective APIs, with dedicated methods for handling transactions. This separation adheres to the single responsibility principle, ensuring that each class focuses solely on its respective payment logic. To connect our unified interface with these diverse implementations, we design adapter classes, PayPal adapter and Stripe adapter. Each adapter converts the method calls from the payment processor interface into the appropriate calls to the underlying payment classes, thus allowing the system to handle both payment types seamlessly. Finally, we demonstrate how clients can use the initiate payment function with both adapters, showcasing their ability to process payments without needing to know the specifics of each payment gateway. This implementation exemplifies how the adapter pattern enables code reuse and flexibility in managing incompatibility between different APIs. In our coffee ordering system, using the decorator pattern, we begin by creating a simple coffee class that has a method to return the base cost of a plain coffee. This foundational class allows us to define the essential functionality of our coffee. To enhance this basic offering, we introduce decorator classes, milk decorator and sugar decorator. Each of these decorators takes an instance of the coffee class as input and modifies the cost method to include the additional price of milk or sugar, showcasing how decorators can dynamically alter behavior. By using these decorators, we can create customized coffee orders without changing the core coffee class. For instance, after initializing a plain coffee, we can wrap it in the milk decorator to add milk, and subsequently wrap the result in the sugar decorator to also add sugar. This flexibility allows us to layer additional features seamlessly, demonstrating the power of the decorator pattern in adding responsibilities at runtime while keeping the original object intact. The approach leads to a modular, maintainable design that easily accommodates future additions if needed. The bridge pattern is designed to separate the abstraction of a class from its implementation, allowing both to evolve independently. Here, we start by defining an abstract class called remote control, which declares two essential methods, turn on and turn off. These methods are placeholders, meant to be overridden by any specific device class that will inherit from remote control. We then create two concrete classes, television and radio, which implement the abstract methods by providing specific behaviors for turning themselves on and off. This illustrates how different devices can have their own unique implementations without complicating the overall design. Next, we introduce the device controller class, which works with any device that conforms to the remote control interface. By accepting a remote control object in its constructor, the device controller can operate any device, calling its turn-on and turn-off methods. This separation allows easy integration of new devices in the future. Finally, we demonstrate the usage of this pattern by creating instances of device controller for both a television and a radio, showcasing how the controller can manage multiple devices flexibly and efficiently. In the following implementation, we illustrate the facade pattern through a home theater system, which integrates several components to create a simplified interface for users. We begin by defining the subsystem classes: projector, screen, and amplifier. Each class represents a part of the home theater system and has methods for performing actions like turning the projector on, lowering the screen, and activating the amplifier. This setup encapsulates the complexity of managing multiple components. Next, we introduce the home theater facade class, which ties these subsystems together. It holds instances of the projector, screen, and amplifier, and provides a single method, watch movie, that invokes the necessary operations to set up the movie experience. When the user calls this method, it sequentially activates the amplifier, turns on the projector, lowers the screen, and prints a message indicating that they can begin watching a movie. By using the facade pattern, we effectively shield users from the intricacies of individual components, promoting a clean and user-friendly interface that streamlines their experience. This design reduces dependencies and enhances code maintainability. In our exploration of the flyweight pattern, we first define a character class that models the shared intrinsic state of game characters. This class includes an initializer that sets the character's name and a display method that formats a string representation of the character. Next, we implement the character factory, which maintains a dictionary of characters. This factory's main role is to ensure that only one instance of each unique character is created. When we call the getCharacter method with a character's name, the factory checks whether that character already exists in its dictionary. If not, it creates a new character instance and stars it. If it does exist, it simply returns the existing instance. This approach not only reduces memory footprint, but also enhances performance by avoiding duplicate object creation. Finally, we demonstrate how the factory operates by creating multiple requests for the character hero. Both requests return the same instance, and a comparison confirms they occupy the same memory space. This illustrates the core advantage of the flyweight pattern, efficient memory usage through shared objects, which is particularly valuable in scenarios requiring numerous similar objects. The proxy pattern serves as an intermediary that controls access to another object, particularly useful for scenarios like lazy initialization. We start with an image interface that outlines the display method, which needs to be implemented by any subclasses. The realImage class represents the actual image. Upon initialization, it loads the image, providing a clear example of eager loading, where resources are consumed immediately even if not needed. In contrast, the proxyImage class acts as a proxy for realImage, holding a reference to it but not instantiating it right away. Instead, it only creates a realImage object when the display method is called for the first time. This lazy initialization significantly optimizes resource usage, as it defers loading until absolutely necessary. When the display method is invoked on proxyImage, it checks if the realImage has been created. If not, it initializes it before delegating the display action. This design efficiently manages resource demands, showcasing the strengths of the proxy pattern in controlling access and improving performance in scenarios where resources may be costly to initialize. As we wrap up our exploration through the implementation examples and use cases of structural design patterns, it's clear how these patterns provide real benefits in software architecture. They enhance code modularity, promote code reuse, and simplify around complex interfaces while addressing common design challenges effectively. By understanding and applying these patterns, you gain mastery over architectural choices that significantly influence the maintainability and scalability of your codebase. Remember, being a proficient developer means knowing not just how to code, but understanding the principles that make your code robust and maintainable. As we transition into behavioral design patterns in our next session, we will explore how to manage object interaction and communication effectively, further enriching our design knowledge. Happy coding! Behavioral design patterns are an essential aspect of object-oriented programming that focus on how objects interact and communicate. Unlike structural patterns, which help in organizing and managing code, behavioral patterns enhance how we manage operations and data flow in our applications. Today, we will dive into the fascinating world of behavioral design patterns, exploring their significance and practical implementations. So far, we've learned about structural design patterns in programming, which include the adapter, decorator, bridge, facade, flyweight, and proxy patterns. These patterns aid in organizing code and enhancing efficiency, allowing for clean, maintainable, and scalable programming solutions. We also discussed how these patterns apply to real-world scenarios, such as payment processing, remote control operations, and image rendering tasks. Now, we will talk about behavioral design patterns, which focus on object interactions and algorithms, and their significance in designing robust software architectures. In this implementation of the chain of responsibility pattern, we define a base handler class that establishes a chain of responsibility among various handlers. Each handler can process a specific type of request or gracefully pass it to the next handler in the chain if it cannot handle it. The technical support and billing support classes inherit from the handler class and include logic to manage requests pertinent to their areas of expertise, such as technical issues or billing inquiries. If they cannot address the incoming requests, they call the super handle request method to pass the request to their successor in the chain. The chain is set up with a technical support instance at the end of the chain and connects to a billing support, thereby effectively allowing billing support to handle general requests as well. In use, when a request is made, the system attempts to handle it according to the defined order of handlers. Depending on what type of issue is presented, be it technical or billing, different outputs will be generated, illustrating the flexibility and decoupling that the chain of responsibility pattern provides in managing varying request types effectively. In this section, we delve into the implementation of the command pattern, specifically designed for a simple text editor. The foundation of this design begins with the command base class, which provides two essential methods: execute and undo. These methods are overridden in the addText command class, which takes an editor instance and the text to be added as parameters. Upon execution, this command invokes the addText method of the textEditor class, appending the specified text to the editor's content. The textEditor class maintains the current state of the text through a content attribute and includes methods for adding and removing text. The removeText function allows the editor to revert the lost addition based on the length of the text removed. The command manager plays a pivotal role in tracking command history, enabling the execution of commands and the functionality to undo the lost command by interacting with executed command objects. This separation of the command's execution from its invocation exemplifies the benefits of the command pattern, streamlining the code architecture for managing text operations efficiently. In this section, we delve into the implementation of the observer pattern through the weather station class and its associated observers. The weather station class acts as the subject, maintaining a list of observers that need to be notified of any temperature changes. When an observer is registered, it gets added to the observers list, while the setTemperature function updates the temperature and invokes the notifyObservers method. This method iterates through each observer in the list, calling their update method to communicate the new temperature value. The displayDevice and WeatherApp classes represent the observers that implement the update method, allowing them to respond dynamically to changes in the weather station. When the temperature is set through the setTemperature method, both the display and application will receive updates, demonstrating the effective decoupling of subject and observers. This architecture allows additional observers to be added or removed without altering the core functionality of the weather station, highlighting the flexibility and scalability of the observer pattern in designing robust software systems. In this part, we explore the state pattern, which is implemented through several classes that define different states of a game character. The base class, state, lays the groundwork by providing a method called handle, which is meant to be overridden by its subclasses. Each state class, standing, running, and jumping, inherits from state and implements the handle method to encapsulate the behaviors associated with that state. The character class utilizes these state classes by maintaining an instance of state and allowing its state to be changed dynamically through the setState method. When the performAction method is called, the character executes the handle method of its current state, which facilitates a clear and flexible transition between states. For instance, upon initialization, the character starts in the standing state and can switch to running or jumping when the corresponding state object is set. This approach alleviates the complications of numerous conditional statements and results in cleaner, more maintainable code as state behaviors become distinct and modular. In this segment, we explore the implementation of the interpreter pattern through a simple home automation command interpreter. The core of this design is the command class, which serves as an abstract base class for all specific command types, such as OpenGate and increaseTemperature. Each specific command class implements the execute method to define its action. For instance, the OpenGate command prints a message indicating that the gate is opening, while increaseTemperature accepts an amount as an argument, allowing for dynamic temperature adjustments. Central to the pattern is the home automation class, which contains the pause-command method that translates string commands into corresponding command objects. This method checks the command string against predefined commands and creates the appropriate command objects based on the input. By instantiating commands directly from strings, the system can easily extend its capabilities. Finally, simulating command execution demonstrates how the interpreter effectively translates user-friendly commands into actionable objects, thus showcasing the principle of separating command logic from the execution process. In this section, we implement the strategy design pattern to introduce different sorting algorithms, allowing us to choose the most efficient method at runtime. We begin by defining a base class called sortStrategy, which contains a placeholder method for sorting. Two concrete classes, QuickSort and BubbleSort, inherit from sortStrategy and provide their specific implementations of the sorting method. The sortedList class serves as a context to utilize these sorting strategies. It initializes with a specific sorting strategy and maintains a list of data. The context class also allows for changing the sorting strategy dynamically through the setStrategy method, promoting flexibility. With methods for adding data and sorting, sortedList seamlessly integrates the strategy chosen. In our example, we first use the quicksort strategy to organize a list of integers. Subsequently, we switch to the bubble sort strategy, demonstrating how easily one can modify the sorting approach without changing the underlying data structure or implementation of the strategies. This encapsulation fosters reusability and the addition of new sorting algorithms as required. In this section, we explore the memento pattern, which provides a way to capture and restore an object's state without exposing its internal structure. The implementation consists of three primary classes: memento, originator, and caretaker. The memento class encapsulates the state of the originator. The originator class is responsible for managing its current state, which can be set and restored using methods designed for saving to and retrieving from memento objects. Whenever the state of the originator changes, it can save its current state by creating a new memento instance, which the caretaker then stores. The caretaker acts as a storage mechanism for multiple memento objects, allowing it to maintain a history of all states. By calling the appropriate methods, the originator can revert to any previous state stored in the caretaker. This pattern effectively supports undo operations, providing a clean way to manage the object's evolution while keeping its internal details shielded from other components. The example provided demonstrates how easily state restoration can be handled in practical applications. In this section, we will delve into the iterator pattern, a key component for traversing collections seamlessly. The code defines two primary classes, collection and iterator. The collection class is initialized with an empty list called items, which will store the elements added to the collection. It includes a method addItem that allows users to append items to this list. The iter method in the collection class is crucial as it returns an instance of the iterator, enabling the collection class to be iterable. The iterator class, on the other hand, manages the current state of iteration with the index attribute that tracks the position within the collection. It implements two special methods: iter, which returns the iterator itself, and next, which retrieves the next item in the collection unless the end is reached, at which point it raises a stop iteration exception. This design encapsulates the iteration logic within the iterator class, allowing the user to traverse through the collection without needing to understand its underlying implementation. This abstraction enhances code readability and maintainability while providing a robust method to manage collections. In conclusion, behavioral design patterns are fundamental for crafting software that is clean, maintainable, and scalable. By functioning as blueprints for communication within software architectures, these patterns help streamline object interactions, range from managing requests efficiently to providing undo mechanisms, and enable flexible behavior in response to various states and commands. Incorporating these patterns into your software projects can drastically improve their architecture and ensure they are built on solid foundations that can handle change with ease. Thank you for joining this exploration of behavioral design patterns. The state design pattern is a significant behavioral pattern in software design that allows an object to alter its behavior when its internal state changes. This enables the object to appear as if it has changed its class, giving the flexibility to manage various states neatly without cluttering the code with complex conditional statements. In this section, we implement the state design pattern through a simple music player application with 3 distinct states: playing, paused, and stopped. The base state class defines the methods play, pause, and stop, which are then overridden in each concrete state class to provide state-specific behavior. For example, in the playing state, invoking the play method will print a message indicating that music is already playing, reflecting the player's current state while transitioning to the appropriate state when pausing or stopping. In the paused state, the play method changes the state back to playing, allowing the music to resume, while the stop method transitions to stopped. The stopped state similarly defines behaviors that inform the user about the actions taken, like preventing a pause when the music is already stopped. This clear structure enables the music player to dynamically alter its behavior based on its state, showcasing the state pattern's effectiveness in managing state-specific functionality without resorting to complex conditionals. Each state class encapsulates the variations in behavior, maintaining clean and maintainable code. In this section, we define the music player class, which serves as the context for managing different states of a music player application. The constructor initializes the player in the stopped state, establishing a clear starting point from which state transitions will occur. The class includes a method named changeState, which allows for switching between different states, thus encapsulating the state management functionality. The methods play, pause, and stop are vital because they delegate control to the current state's behavior. When invoked, these methods execute the corresponding action defined in the current state object and potentially transition to a new state if required. For instance, if the player is in the stopped state and the play method is called, it will transition to the playing state. This delegation of responsibility not only enhances the code's readability, but also adheres to the single responsibility principle, as each state handles its own behavior. This structured approach simplifies future code maintenance and allows for easy expansions, making it straightforward to incorporate additional states or functionalities as needed. In this section, we simulate user interactions within the music player application, demonstrating the practical utility of the state design pattern. The code initializes a music player instance, which starts in the stopped state. When the play method is called, the player transitions to the playing state, outputting a message indicating that the music has started. When the pause method is executed next, the player changes its state to paused and notifies the user that it is pausing the music. Further interactions continue to showcase the dynamic behavior of the music player. Calling stop transitions the player to the stopped state, while invoking play again resumes the music. Each action reflects how the music player's state impacts its responses, illustrating the flexibility that the state pattern provides. By clearly defining behaviors within each state, we avoid complex conditional logic, which enhances code maintainability and readability. This approach exemplifies the strength of the pattern in managing state-dependent behaviors seamlessly and efficiently, reinforcing the concepts we've explored. In this section, we introduce the buffering state for the music player class, which enhances its functionality by allowing it to handle scenarios where music is temporarily unavailable due to buffering. The buffering class inherits from the base state class, ensuring it remains consistent with the other states in terms of interface. Within this class, the play method informs the user that the music is currently buffering, and once the process is complete, it transitions back to the playing state. This smooth transition demonstrates how the state can dynamically adapt to varying conditions. The pause method communicates that pausing is not possible during buffering, emphasizing the constraints inherent to this state. Finally, the stop method provides feedback when the buffering action is halted, transitioning the music player to the stopped state when necessary. Overall, implementing this buffering state illustrates the powerful extensibility of the state pattern, enabling developers to enrich the application's capabilities with minimal disruption to existing code, thereby maintaining clarity and robustness in state management. In this section, we implement a vending machine that utilizes the state pattern, allowing the machine to operate in different states effectively. The vending machine class starts by setting its initial state to waiting for selection, which means it's ready to accept user input. The class provides methods to change its state, select an item, and dispense selections. When an item is selected, the current state select item method is invoked, indicating that a choice has been made, and this typically transitions the machine to the dispensing state. In the waiting for selection state, selecting an item triggers a confirmation message and changes the state to dispensing, while the dispensing state manages the actual dispensing of the item and then reverts back to waiting for selection, ready for the next interaction. This structure keeps the logic organized and each state focused solely on its specific behavior. The modular design allows for easy extensions, where new states can be added with unique behaviors, enhancing flexibility without complicating the overall implementation. This pattern demonstrates the power of state management, allowing for clean transitions and minimizing the need for conditional statements throughout the code. The state pattern also supports testing changes in behavior across the application's lifecycle. In a system like our music player, if the requirement evolves to handle a network streaming service, we need only extend our state implementations. Whether we consider latency or error states, modifying or adding new states becomes straightforward without the need to rewrite existing logic. Always keep in mind the importance of clear and intuitive state transitions. When designing your states, ensure the flow between states is logical and informative. Consider implementing diagrams that outline state transitions, which not only guide programmers, but can also assist in onboarding new team members who need to grasp the system's behavior swiftly. In conclusion, the state design pattern is a powerful tool for managing stateful behavior in a flexible and maintainable way. By using a combination of a base state class and specific concrete state classes, developers can create robust systems that can effortlessly adapt their behavior according to their internal states. This encapsulation fosters clean code, enhances readability, and greatly simplifies the management of complex behavior within applications. We're now equipped to handle state transitions effectively, and as we continue exploring further behavioral patterns, you'll see how the state pattern beautifully integrates with them to create even more powerful architectures. Thank you for joining me today in this deep dive into the state design pattern. As you practice implementing these concepts, remember to think about how they can streamline your application's behaviors and improve overall maintainability. Happy coding! In our interpreter design, we start with an abstract base class called expression. This class serves as the foundation for all specific expressions we will create for our domain-specific language. It contains an abstract method named interpret, which is meant to be overridden by subclasses. This method will encapsulate the logic required to evaluate different types of expressions. The beauty of this design lies in its extensibility. As we derive new classes from expression, each subclass will implement its own interpretation logic. This allows us to build a hierarchy of expressions, making it easier to manage and execute complex arithmetic operations. Each concrete class can encapsulate specific behavior for its operation, whether it's addition, subtraction, multiplication, or division, ensuring that the overall structure remains clean and maintainable. By adhering to this structure, we not only define a clear grammar for our language, but also facilitate the process of parsing and interpreting various expressions, paving the way for a modular and scalable interpreter. In this part of our interpreter pattern implementation, we will define the addition class responsible for executing addition operations in our expression language. This class extends the base expression class, which establishes the foundation for all expression components. The constructor of the addition class accepts two parameters, left and right. These represent the expressions to be added. By holding references to these expressions, the addition class can effectively manage complex arithmetic operations composed of simple parts. The core functionality resides within the interpret method. Here, we leverage the power of recursion by invoking the interpret method on both left and right expressions. This returns their evaluated values, which we then sum together. This approach not only allows the addition class to evaluate direct expressions like 5 and 3, but also more composite expressions built from other operations, fostering a modular structure that enhances readability and maintenance. By implementing this class, we empower our interpreter to handle addition seamlessly, forming a crucial part of the overall expression tree. Next, we create a subtraction class that extends our expression base class. This class is responsible for handling subtraction operations by taking in two expressions as parameters, the left and right operands. The constructor initializes these operands, and when the interpret method is called, it evaluates both operands recursively using their respective interpret methods, returning the result of subtracting the right operand from the left. Following this, we introduce the number class, which also extends the expression class. This class serves a distinct purpose by representing literal integer values. When instantiated with a specific integer, it simply stores that value. The interpret method for this class directly returns the stored integer, allowing it to be integrated seamlessly into more complex expressions. Together, these classes form the foundation for an expression tree, enabling the interpretation of arithmetic operations. By encapsulating the logic for each operation and operand, we can construct intricate expressions effortlessly, thereby illustrating the power of the interpreter design pattern in creating a simple yet flexible DSL for arithmetic calculations. In this section, we construct and evaluate a complete expression using our interpreter pattern implementation. Here, we begin by creating a complex expression, 5 plus 3, 2, 1. First, we instantiate the addition class, passing in two number instances representing the integers 5 and 3. This addition instance will interpret its operands and return their sum. On the right side of the main subtraction, we create another subtraction instance, which encapsulates two more number instances for 2 and 1. This structure allows us to compute 2, 1, which the subtraction class will handle by invoking the interpret method on both number instances. Finally, we encapsulate both the addition and the nested subtraction within another subtraction instance, creating a complete expression tree. When we call the interpret method on this overall expression, it traverses the tree, computing the result by recursively interpreting each component. This showcases not only the power and flexibility of the interpreter pattern, but also how easily we can create and evaluate complex arithmetic expressions through simple class interactions. To expand our arithmetic expression interpreter, we introduce the multiplication and division classes. These classes adhere to the same structure we established with addition and subtraction, ensuring consistency in how we interpret expressions. The multiplication class takes two expressions as input and overrides the interpret method to multiply their results. This allows us to combine basic operations into more complex evaluates. On the other hand, the division class also accepts two expressions, but adds a critical safeguard. It checks if the right expression evaluates to 0 before performing the division. This error handling is essential to prevent runtime exceptions, demonstrating the importance of robustness in our code. With these new classes in place, we can create expressions that incorporate multiplication or division seamlessly alongside other operations. For instance, this modular approach allows us to construct and evaluate intricate expressions involving multiple types of arithmetic operations, significantly enhancing the functionality of our interpreter while keeping the design clean and maintainable. This illustrates the power and flexibility of the interpreter design pattern in creating a DSL for arithmetic calculations. In this part of our tutorial, we delve into executing more complex expressions using our interpreter classes. The expression 5 plus 3, 10/2, 2, 1 showcases the combined use of addition, multiplication, division, and subtraction. We begin by creating an instance of subtraction to represent the outer subtraction operation, which takes two arguments, the result of the multiplication and the result of another subtraction. The left side consists of a multiplication instance that multiplies the outcome of adding 5 and 3 together with the result from dividing 10 by 2. Each arithmetic operation is encapsulated within its respective class, ensuring they can be evaluated in isolation through their interpret methods. For instance, the addition of the number instances represents the operands 5 and 3, while the division checks for division by 0 before returning the calculated result. This structured approach allows us to effectively maintain and extend our expression language, enabling a clearer representation of complex mathematical operations within our DSL, illustrating the power of the interpreter pattern in creating robust and flexible parsers for domain-specific languages. In a more advanced use case, you might encounter situations where you need to handle operator precedence or parentheses. You can enhance the current implementation by introducing a parser class responsible for analyzing text input and producing your expression tree structurally. This parser would read a source string character by character, indicating when to create new operation objects based on the grammar rules defined at the start. This is where your design can become more sophisticated, possibly integrating techniques such as shunting yard algorithms to convert infix notation to postfix for easier evaluation. In conclusion, the interpreter design pattern is a powerful tool for defining and interpreting domain-specific languages. By establishing a grammar and creating classes to represent expressions and operations, we can effortlessly parse and evaluate complex logic. The pattern's modularity makes it easy to add new operations and handle complexities, paving the way for future extensions and improvements. As you implement interpreters in your projects, remember to keep the grammar well-structured and consider how you want to manage precedence and error handling. This will ensure your interpreter remains robust, flexible, and easy to maintain over time. Thank you for joining me in exploring the exciting world of the interpreter pattern, and happy coding. Architectural patterns are crucial in software development, offering a blueprint for solving common problems in system architecture. In our previous discussions, we focused on behavioral patterns, which involve the interactions and responsibilities between objects. We dived into specific patterns like the interpreter design pattern, which is instrumental in crafting domain-specific languages. This foundation has paved the way for our understanding of architectural patterns. So far, we learned about defining classes for operations in DSLs that pave the way for expression trees, allowing us to handle complex expressions robustly. Now, we will transition into the world of architectural patterns and understand how these structures can enhance our software system's scalability, maintainability, and overall design. In this section, we explore the item class, which forms a crucial component of the model in our MVC architecture, representing an inventory item. The init method initializes each item with a name and a quantity, establishing the foundational data structure for our application. The update quantity method allows for dynamic changes to the inventory, enabling us to increase or decrease an item's quantity based on user input, which is essential for managing stock levels effectively. Furthermore, the SDR method provides a user-friendly string representation of the object, making it easier to display item details when needed. This encapsulation of data and behavior illustrates the principles of object-oriented design, where the item class not only holds data, but also contains methods that manipulate that data in a meaningful way. By implementing such a structure within our model, we ensure that our application's business logic is neatly contained, promoting maintainability and scalability as our application grows. In this section, we focus on the implementation of our view component within the MVC architecture, highlighting how it interfaces with the user and presents data. The console view class is crafted to manage the display of inventory items and messages, encapsulating presentation logic separately from the business logic found in the model. The display item method within the console view class takes an item object as an argument and prints its representation in a user-friendly format, clearly showing the inventory status. This method helps ensure that the user can easily understand the current stock of items without delving into the underlying data structures. Moreover, the showMessage method is designed to output any generic messages that may need to be communicated to the user, allowing for feedback or alerts in a console environment. This modular approach, where the view is decoupled from the model, promotes flexibility. If we later decide to implement a graphical interface or web-based display, we can modify the console view without altering the core business logic that resides in the model. This separation enhances maintainability and adaptability throughout the application's development lifecycle. In this section, we delve into the inventory controller, which is pivotal in managing interactions between the model and the view in our inventory application. The constructor method initializes the controller with references to the model, which contains our item data, and the view, which is responsible for displaying information to the user. The addItem method is designed to facilitate the addition of new inventory items. When called, it creates a new instance of the item class using the provided name and quantity, appending this instance to the model. Following this, it invokes the displayItem method of the view to present the newly added item in an easy-to-read format, demonstrating how controllers bridge user actions and backend data management. Another important method is updateItem, which allows for the modification of existing inventory items. It iterates through the items in the model, searching for the one that matches the given name. If found, it updates the item's quantity using its method and notifies the view to update its display. If the item cannot be located, a user-friendly message is shown to indicate that the operation was unsuccessful. This design encapsulates the complexities of user interactions, maintaining a clean separation of logic. In this section, we define the gRPC service for processing payments using protocol buffers. The syntax begins with specifying proto3, which denotes the version of protocol buffers used. The package name, payment, organizes the service and message types logically. The core of this code is the payment service, which declares an RPC method named processPayment. This method facilitates communication between the client and server, taking a payment request and returning a payment response. This clear interface ensures that both sides of the gRPC communication understand the data structure being passed. The payment request message outlines the necessary information required for processing a payment, including ordered, amount, currency, and userid, each tagged with a unique identifier for serialization. Meanwhile, the payment response message reflects the result of the payment process, containing attributes for paymented and status, allowing clients to determine if the operation succeeded or failed. This design enhances the clarity and error handling of payment processes in microservices architectures, enabling teams to easily manage and scale payment functionalities independently. In this section, we will implement the logic for a payment processing service using gRPC. The code defines a payment service class, which inherits from payment service servicer, enabling it to serve gRPC clients with the defined methods. Inside the processPayment method, we have a simulated payment logic where we generate a unique payment ID and set the payment status to success. This method is essential as it encapsulates the core functionality of processing payments and returns a structured response to the client using payment response. The serve function sets up the gRPC server. It creates a server instance with a thread pool to handle multiple simultaneous requests efficiently, which is crucial for high-traffic environments like e-commerce. The service is registered with the server, allowing it to listen for incoming requests on port 50,051. Finally, the main block ensures that the server starts running when the script is executed, maintaining active listening for any payment processing requests. This architecture enables seamless communication between services, exemplifying the advantages of a microservices approach in modern applications. In this segment, we're examining a basic Oz Lambda function that processes events triggered by file uploads to an S3 bucket. The function is defined with Lambda handler, which receives two parameters, Event and context. The event parameter contains crucial information about the upload, encapsulating details like the file name and the bucket name in a structured format. We access this information through the event dictionary, where the file name is retrieved from the first record's S3 object key and the bucket name from the associated bucket. Upon successfully extracting these details, the function returns a JSON response, embedding a message that confirms the upload. The response includes a status code of 200, indicating the operation's success. This structure not only allows for easy integration with other OS services, but also ensures that the function's output is appropriately formatted for user interfaces or logging mechanisms. By utilizing event-driven architecture, this Lambda function efficiently handles file uploads, showcasing the benefits of serverless solutions in reducing both overhead and operational complexity. In this section, we implement an event sourcing pattern with a simple bank account class that captures financial transactions as events. The class initializes with a balance set to 0 and an empty event list to keep track of all actions taken on the account. When a user makes a deposit or a withdrawal, the respective method is invoked, which in turn calls the applyEvent method. This method processes the event by checking its type, whether it's a deposit or a withdrawal, and updates the account's balance accordingly. Each action is then logged as an event in the events list, ensuring a historical record of all transactions. This logging of events is pivotal in event sourcing, as it allows us to reconstruct the account's state at any point in time simply by replaying the recorded events. Consequently, this design not only simplifies debugging and extending the system, but also provides a clear, auditable trail of the account's activities, embodying the principles of robust software architecture. In summary, architectural patterns play a substantial role in modern software development. They provide structured approaches to designing systems, facilitating better maintenance, scaling, and collaboration across development teams. By exploring patterns such as MVC, microservices, serverless, and event sourcing, we equip ourselves with versatile tools to tackle diverse software challenges, ensuring our creations are robust, efficient, and ready for future demands. In our next discussions, we will dive deeper into concurrency and asynchronous patterns, focusing on techniques that allow our programs to manage multiple operations and enhance performance. Thank you for tuning in, and I look forward to our next session together. In today's lesson, we're diving into the world of microservices, an architectural style that is transforming the way developers build and maintain applications. This approach fosters greater flexibility, scalability, and resilience compared to traditional monolithic structures. So far, we learned about the significance of architectural patterns in software development, specifically focusing on the Model View Controller, MVC pattern, which segregates applications into 3 components for modularity and scalability. We explored the roles of the model, view, and controller in managing data, presenting information, and handling user input, respectively. Additionally, we introduced the microservices architecture, which enhances flexibility by breaking applications into independent services that communicate via APIs. Lastly, we touched upon the serverless pattern and event sourcing, underscoring their advantages in management, cost efficiency, and maintaining historical state changes. Now we will cover the overview of microservices, detailing its characteristics, benefits, and implementation strategies. Traditionally, developers working on building a server-side application have been using a single codebase, implementing all or most functionalities right there through common development practices. This monolithic architecture means everything is interconnected, making it challenging to manage. Any small change could inadvertently affect other parts of the system. In this example, we create a simple inventory management microservice using Flask, a lightweight web framework for Python. The core functionality of this service revolves around managing an inventory of items through res tfol endpoints. We start by initializing the Flask application and creating an empty inventory dictionary to store item data. The first endpoint allows clients to add an item to the inventory using a POST request to inventory. When a request is made, the service extracts the item data from the request's JSON body, assigns it to the inventory using the item's unique identifier, and responds with a confirmation message along with a status code indicating successful creation. The second endpoint enables retrieval of an item by its ID through a GET request. Upon receiving a request, the service checks if the item exists in the inventory. If found, it returns the item data. Otherwise, it provides an error message indicating that the item was not found. This simple structure not only highlights the essential CRUD operations, but also demonstrates how individual microservices can independently handle specific functionalities, paving the way for greater scalability and maintainability. In this section, we focus on how to deploy a microservice using Docker, which streamlines the process of managing application components. The command provided initiates a Docker container for the payment service, specifying essential parameters like the container name and part mappings. The D flag runs the container in detached mode, allowing it to operate in the background without blocking your terminal. By using name payment service, we assign a clear identifier for easy access and management of this specific container. The P8080 option maps the container's internal part 8080 to the host's part 8080, thereby facilitating external access to the service. This setup enables the payment service to handle incoming requests seamlessly and ensures that multiple instances of the service can be launched as needed. By encapsulating the payment processing functionality in this containerized environment, we benefit from consistent deployment, simplified resource management, and the ability to scale this microservice independently as demand fluctuates. This mechanism is essential in a microservices architecture, where each service must remain flexible and responsive to varying loads. In this section, we implement the circuit breaker pattern, a crucial technique for handling service failures gracefully in a microservices architecture. The circuit breaker class is designed to monitor service calls and manage failures effectively. When we initialize the class, we set a failure threshold and a recovery time. The failure threshold determines how many consecutive failures must occur before the circuit breaker opens, while the recovery time defines how long we will wait before allowing service calls to be attempted again. The class maintains a count of failures and records the last failure time to manage the state of the circuit breaker. The call service method is where the logic happens. Before attempting a service call, the method checks if the failure count has reached the threshold. If it has, and if sufficient recovery time has not passed, an exception is raised to indicate that the circuit is open and requests should not be processed. If the service call is attempted and fails, we increment the failure count and update the lost failure time. This implementation enhances system resilience, ensuring that a failing service does not continually affect the broader application. In this section, we'll look at a simple gRPC service definition for an auto placement functionality. The service is defined using protocol buffers, a language-agnostic way to serialize structured data, which makes it suitable for gRPC services. The definition starts with the syntax equals proto3 line, indicating that we are using version 3 of protocol buffers. The package order line specifies the namespace for the generated code to prevent naming conflicts. Next, we declare the auto service, which exposes a remote procedure call RPC named placeOrder. This RPC takes an auto request message as input and returns an auto confirmation message, illustrating the request response paradigm of gRPC services. The auto request message is structured with two fields: itemid, a string to denote the product's identifier, and quantity, an integer to specify the amount to order. The auto confirmation message provides feedback on the auto placement, including an ordered and a Boolean success flag, signaling whether the operation was successful. This clear structure helps in translating messages over the network efficiently, enabling seamless communication between the order and inventory services. In this section, we are implementing a monitoring solution using Prometheus to track service metrics in a microservices architecture. The first line of the code initializes an HTTP server on port 8000 to expose the metrics endpoint, which enables Prometheus to scrape metrics data for analysis and visualization. Next, we create a metric called request time, designed to track the duration of request processing in seconds. By using the summary type from the Prometheus client, we can capture aggregate data points, helping us identify performance trends over time. The decorator above the process request function automatically records the time taken to execute this function, simulating request processing through a sleep operation, which stands in for any real business logic. Finally, the code enters an infinite loop where it continually calls the process request function, allowing for ongoing metric generation. By deploying this code, you can gain valuable insights into the performance of your microservices, aiding in performance tuning and ensuring reliability in production environments through real-time metric visualization in tools like Grafana. In this section, we will explore the concept of event publishing in a microservices architecture through a simple code implementation. The event publisher class serves as a utility for sending events to a messaging system, which is crucial for enabling communication between different services. The main function in the class, publish event, takes an event as its parameter and sends it to a message broker or event bus, ensuring that other microservices can react to the event accordingly. This functionality is vital for maintaining data consistency across services. When a significant event occurs, such as an order being placed, it allows subscribed services to update their states or perform necessary actions. In the example provided, an event is defined in a dictionary format that includes the type of event and its associated data, such as the order ID. By creating an instance of event publisher and invoking publish event with this event, the code demonstrates how a microservice can publish an event seamlessly, enabling event-driven workflows in your application and promoting independence and scalability among microservices. This pattern enhances responsiveness and integrity in distributed systems, fostering a robust architecture. In conclusion, the microservices architecture represents a significant shift in how we conceive software development. By breaking applications into smaller, manageable components, we gain flexibility, scalability, and resilience. The independent nature of microservices allows different teams to work on various aspects of the application simultaneously, speeding up development and deployment cycles. As we've discussed, while this approach comes with its unique set of challenges, like data management and service communication, it ultimately offers a modern solution to meet the complex demands of today's software requirements. So, as you venture into the world of microservices, remember that each service should be small, focused, and well-defined. Invest in automation and orchestration to manage these services at scale, and leverage the strengths of individual technologies that best fit your application's needs. Thank you for tuning in, and I look forward to our next discussion where we will explore even more exciting topics in software engineering. Understanding event sourcing can dramatically enhance how we manage state changes within applications. Essentially, this pattern allows us to store state changes as a sequence of events, making it possible to reconstruct past states and providing a clear audit trail of every action taken. In our tutorial today, we will unpack what event sourcing is, how it works, and its applications in modern software development. So far, we covered microservices as a transformative architectural style that enhances application flexibility, scalability, and resilience compared to traditional monolithic structures. We emphasized the importance of breaking down applications into independent services, each responsible for specific business functions, and discussed advantages like technology stack flexibility and efficient scaling. Additionally, we explored key concepts such as resilience through error isolation, service communication methods like REST and gRPC, and challenges related to monitoring and data management in a microservices architecture. Now, we will delve into event sourcing, examining its core principles, benefits, and and a practical implementation. In this section, we'll delve into the SQL commands used to implement the database structure for our banking application, specifically focusing on the tables supporting event sourcing. The first command creates an accounts table, which holds critical details about each account, including a unique identifier, ID, and its current balance. By using a primary key on the ID, we ensure that each account can be distinctly recognized, making transactions and retrievals efficient. Next, we define the account events table. This structure is essential for event sourcing, as it stores every action related to account changes, like deposits and withdrawals, along with important metadata. Each row in this table includes a unique identifier for the event, a reference to the associated account, the type of event, indicating whether it's a deposit or withdrawal, the amount involved, and a timestamp marking when the event occurred. This comprehensive design not only allows us to track the complete history of account activities, but also facilitates detailed auditing and debugging, empowering us to investigate discrepancies in account balances by replaying relevant events. To implement event sourcing in our banking application, we start by defining core event classes that represent account activities. The account event class serves as a base class that encapsulates shared properties such as accounted, event type, amount, and created at. This design promotes code reuse and organization. We then define specific event classes, deposit event and withdrawal event. Each of these subclasses inherits from account event and initializes the event type attribute to distinguish between deposit and withdrawal actions. This inheritance hierarchy enables us to easily manage different event types while maintaining a clear and structured approach to event handling. By organizing our events this way, we lay the groundwork for efficient event management in the application. When a transaction occurs, an instance of either deposit event or withdrawal event can be created, representing a specific change in account state. This structure not only enhances clarity, but also facilitates the subsequent processing of events as we build out the account services functionality to handle these events logically. Overall, this architecture ensures that we can track all changes made to an account in a reliable and maintainable manner, which is fundamental for the principles of event sourcing. In the implementation of our account service class, we establish a robust mechanism for managing user account balances through event handling. The class is initialized with a dictionary to track the balances for each account, ensuring we can efficiently retrieve and update these values as events are processed. The handle event method serves as the central point for managing different types of account events. It checks the event's type, determining whether to apply a deposit or a withdrawal. This separation of concerns allows for cleaner code and smoother integration of event handling into the overall application structure. To process deposits, the private method applyDeposit first checks if the account exists in our dictionary. If not, it initializes the account balance to 0, then adds the deposit amount. Similarly, the applyWithdrawal method follows the same pattern, subtracting the specified amount from the account balance while ensuring the account is initialized. This approach exemplifies the encapsulation and organization of code, adhering to best practices in software development by isolating event handling from other system components. Overall, this modularity enhances maintainability and clarity within our application architecture. In our implementation of event sourcing, we have defined an account class responsible for managing account balances by loading and processing related events. The constructor initializes the object with a specified account ID and sets the initial balance to 0. The loadEvents method is essential for reconstructing the current balance of the account. It takes a list of events as an argument, iterating through each one to update the balance accordingly. Specifically, when a deposit event is encountered, the corresponding amount is added to the balance, effectively reflecting an increase in funds. Conversely, when a withdrawal event is processed, the amount is subtracted, reflecting a decrease in available funds. This sequential processing of events ensures that we can accurately derive the account's balance despite the order or volume of transactions. After loading and applying all relevant events, the account balance is printed, demonstrating how the implementation utilizes event data to maintain an up-to-date and accurate financial state, showcasing the power of event sourcing in maintaining a comprehensive audit trail of all financial activity. The benefits of adopting event sourcing in your applications are numerous. For one, it vastly simplifies debugging and auditing processes. Since all state changes are recorded through events, tracking down how and why a particular state was reached becomes straightforward. You have the entire timeline of actions at your disposal, providing transparency and accountability. Moreover, this pattern facilitates the handling of complex business transactions. If your application needs to support multi-step transactions, you can implement compensating actions through events. For instance, if a withdrawal event is followed by a cancellation event, you can have a special method that negates the previous withdrawal, ensuring your system remains consistent. Another advantage lies in your ability to experiment with future changes. By replaying past events, you can test new features or optimizations while ensuring that your state reconstruction remains intact. This means you can evolve your system without worrying about losing critical historical data. The following code snippet demonstrates how to effectively implement snapshotting within an account management system using event sourcing principles. The account class serves as the central component for managing account-related information. When an account is instantiated, it requires an accounted and initializes its balance to 0. The snapshot method plays a crucial role as it captures the current state of the account, including the account ID, balance, and a timestamp. This is particularly useful for preserving the account state at a specific moment without needing to process all historical events. By returning this information in a structured format, it enables efficient state retrieval. Conversely, the load snapshot method allows for restoring a previously saved state. By accepting a snapshot as its parameter, it updates the account's balance to the one stored in the snapshot. This method streamlines the process of re-establishing the account state, enhancing performance and simplifying data recovery when necessary. Overall, implementing these methods provides a robust mechanism for managing account state within the broader event-driven architecture, addressing complexities associated with data growth and operational efficiency. In conclusion, event sourcing is not just a technical choice. It's an architectural paradigm shift that can redefine how we think about state management in applications. By storing state changes as a sequence of events, we gain the distinct advantages of auditability, flexibility, and complexity management. As we've discussed, event sourcing fits beautifully in the context of microservices, where managing state across multiple services can become a daunting task. To summarize, undertaking the journey of implementing event sourcing requires careful consideration, but the benefits often outweigh the complexities involved. As you think about your applications and architectures, event-driven approaches could provide the robustness and resilience needed to thrive in today's digital ecosystem. With that knowledge in your toolkit, you're better equipped to innovate and improve your software solutions. Thank you for joining me in this exploration of event sourcing. In our journey through software architecture, we've explored intriguing concepts and methods to tackle complex challenges. So far, we have delved into event sourcing, focusing on how it entails capturing state changes as events. This opens the door to reconstructing historical states, providing a robust audit trail, and improving auditing capabilities in applications like banking systems. Now, we'll pivot our focus to concurrency and asynchronous patterns, a critical area in software design that enhances performance and user experience. Concurrency represents the ability of a program to manage multiple operations simultaneously, efficiently utilizing multi-core processes. Image a busy restaurant where several chefs are preparing different dishes at the same time, but with a clear organization ensuring that each dish is served fresh and hot. This is akin to how concurrency functions in programming. Asynchronous programming complements this by allowing a program to handle other tasks instead of being blocked while waiting for an operation, such as a request to a server. In this section, we will examine the implementation of a thread pool using Python's Concurrency module. The code begins by importing the necessary libraries, specifically thread pool executor for managing the thread pool and time for simulating task duration. The task function is defined to represent individual units of work, taking a single parameter n. Inside this function, we print a message indicating the start of task execution, followed by a call to time, sleep 1, to simulate a time-consuming operation. After the sleep duration, we print a completion message for that specific task. Within the with statement, we instantiate a thread pool executor with a maximum of 5 worker threads. This is where the thread pool is managed, allowing tasks to run concurrently. A loop is employed to submit 10 tasks to the executor. Each task is submitted using the executorSubmit method, which assigns the task function to be executed with the respective task number, I. This design allows the worker threads to efficiently pick up available tasks from the queue, exemplifying concurrency as multiple tasks execute in parallel, enhancing the overall performance of the application. In this section, we delve into the worker model pattern using Python's multiprocessing library to efficiently handle tasks across multiple processes. The code begins by defining a worker function that continuously processes tasks from a queue until there are no tasks left. Each worker retrieves a task using the get method from the task queue, simulating some work with a brief sleep period to represent the processing time involved. This setup allows for clear task management, as the queue holds the tasks waiting to be processed. In the main function, we create a queue and populate it with 10 distinct tasks. Importantly, we start 5 worker processes, each of which functions independently, demonstrating parallel processing. Once the workers are initiated, the main program waits for all workers to finish their tasks with join, ensuring that it only proceeds once all tasks have been fully processed. This effective management of task execution exemplifies the worker model's capacity to distribute workloads, highlighting how concurrent processing can enhance performance in any application requiring task division. The script concludes by informing the user that all tasks have been successfully completed. In this example, we utilize the thread pool executor from the Concurrency module to demonstrate asynchronous programming with the future and promise pattern. First, we define a simple function called square, which takes a number and returns its square. This function will be executed multiple times concurrently. Next, we create a thread pool executor context manager that manages a pool of threads. Within this context, we submit tasks to the executor using a list comprehension, where we pass numbers from 1 to 3 to the square function. Each submission returns a future object that represents the execution of that task. Finally, we use the asCompleted function to iterate over the future objects as they complete. This allows us to handle the results in the order they finish, rather than the order they were started. By printing each result as it becomes available, we illustrate the non-blocking nature of the code, enabling our application to remain responsive even while performing potentially long-running calculations. This approach enhances usability, particularly in applications requiring efficient management of computational tasks. In this example, we explore how to utilize Python's Asyncio library to perform asynchronous programming effectively. The code begins by importing the Asyncio module, which is essential for creating and managing asynchronous tasks. We define a coroutine named square, which takes an input and simulates an I/O-bound operation using Asyncio, sleep. This non-blocking feature allows the program to pause for a second without blocking other operations, making it ideal for I/O tasks. The main coroutine serves as the entry point, where we create a list of tasks that call the square coroutine for values ranging from 1 to 3. By using Asyncio, gather, we efficiently collect all the results concurrently, demonstrating how multiple coroutines can run simultaneously within a single thread. The gathered results are then printed in sequence, highlighting the ease of handling asynchronous operations in a structured manner. Finally, Asyncio, run, main, executes the main coroutine, showcasing the practical use of this library in building responsive applications that can manage multiple tasks effectively. In the given code, we implement the observer pattern using ReactiveX, allowing us to create an observable stream of data updates. First, we import the necessary modules from the ReactiveX library, which provides a robust framework for asynchronous programming. The observe function is where the magic happens. It creates a source observable using rx, interval 1, emitting a new value every second. The pipe method is used in conjunction with opsmap to transform these emitted values into a formatted string, prefixed with update. Next, we subscribe to this observable stream with a lambda function that prints the emitted value to the console. This subscription establishes a direct connection between the source of data and its subscribers, ensuring that every emitted update is immediately printed out. By invoking the observe function in the main block, the program starts streaming updates in real time. This simple setup illustrates the strength of reactive programming, where changes in data state trigger instantaneous responses, perfectly aligning with the principles of asynchronous programming and enhancing interaction with real-time data scenarios. Concurrency and asynchronous patterns form the backbone of efficient, responsive software applications. By leveraging patterns such as thread pools, worker models, futures, and the observer pattern, you can significantly enhance performance and user satisfaction. As we wrap this up, think of how these principles can be applied to your own projects, allowing for scalable, maintainable systems that meet user demands efficiently. This knowledge is not just theoretical, it's immensely practical for the next generation of software architecture. Understanding the future and promise pattern is essential for mastering asynchronous programming. This concept allows developers to create applications that remain responsive, even while waiting for operations to complete. It's a game changer in application architecture, enabling a smoother user experience. So far, we learned about important concepts in software architecture, including event sourcing, concurrency, and asynchronous patterns, and how asynchronous programming facilitates smooth operation by allowing tasks to run in the background. Now, we will dive deeper into the future and promise pattern, exploring its mechanisms, applications, and benefits. In this section, we focus on a practical example that illustrates asynchronous data retrieval using Python's Asyncio library. The fetch data function simulates an asynchronous operation by first printing a message to indicate that data is being fetched. It then introduces a 2-second delay to mimic network latency, after which it randomly decides to either return a success message or raise an error. This randomness helps demonstrate how asynchronous programming can handle unpredictable outcomes. The main function serves as the entry point for executing our asynchronous tasks. Here, it calls fetchData and uses the await keyword to pause execution until the promise is fulfilled. If the operation succeeds, the result is printed. However, if an error occurs, it is caught by the except clause, which then prints the error message. This structured approach to handling asynchronous operations not only clarifies the flow of data retrieval, but also exemplifies the importance of error handling in asynchronous programming, ensuring that even when problems arise, the program maintains clarity and stability. In this section, we expand our understanding of chaining asynchronous operations using promises. The fetchUserDetails function illustrates how to retrieve additional data after the initial operation has completed. It simulates fetching user information, awaiting a short delay to represent the asynchronous nature of the task. Next, the mainWithChain function orchestrates the flow of this chaining process. It begins by calling the fetchData function, which retrieves initial data and prints it out. Upon successful completion of this operation, it proceeds to invoke fetchUserDetails, allowing for a seamless transition to gathering user-specific information. This structure demonstrates effective error handling as well. Should any of the asynchronous calls fail, the except block captures the error and prints a relevant message, maintaining the integrity of the application flow. By utilizing async and await, we ensure that our code remains clear and manageable. The overall pattern emphasizes how promises facilitate organized and readable asynchronous workflows, showcasing the robustness of error management while chaining multiple operations. In this segment, we will explore an advanced approach to error handling in asynchronous programming using promises. The fetchUserDetails advanced function simulates an asynchronous operation that attempts to retrieve user details. It introduces a brief delay before deliberately raising a value error, simulating a failure scenario when fetching data. This is an important aspect of the promise pattern, handling potential errors gracefully. In the mainWithErrorHandling function, we initiate the data fetching process. The use of a try-except block allows us to manage this asynchronous operation effectively. If the fetch data call succeeds, its result is printed, followed by a call to fetchUserDetails advanced, demonstrating the chain of operations. Should an error occur at any point, such as failing to retrieve user details, the control moves to the accept block. Here, we catch the value error and display a clear error message, making it easier for developers to understand what went wrong. This organized error management keeps the code clean and maintainable, reinforcing how the promise pattern enhances error handling in asynchronous programming. In this section, we will explore how to leverage the Asyncio gather function to enhance our asynchronous programming capabilities by fetching multiple datasets concurrently. The code begins by defining two asynchronous functions, fetchData1 and fetchData2, which simulate data retrieval with specified delays using awaitAsyncio sleep. The first function introduces a delay of 1 second, while the second introduces a 2-second delay before returning their respective data strings. Next, the fetchMultipleData function is defined, showcasing the power of Asyncio gather. This function concurrently calls both fetchData1 and fetchData2, effectively reducing the total time for execution to that of the longest individual call, rather than the cumulative time of both. This illustrates a key benefit of the future and promise pattern in managing asynchronous tasks, as it allows for more efficient use of time when performing multiple operations. Upon completion, the results are collected into a list and printed, demonstrating how Asyncio gather makes it easy to work with outcomes from multiple coroutines concurrently. This method makes your code cleaner and significantly enhances performance in real-world applications that require concurrent data fetching. To wrap it up, let's consider promises' role in modern web applications. Today, with the rise of single-page applications and real-time features, the need for clean, efficient asynchronous handling is paramount. The future and promise pattern not only enhances user experience, but also simplifies developers' lives by providing robust methods for managing operations that might take an indeterminate amount of time. When using frameworks like React, Angular, or Vue.js, promises are ingrained into the data fetching processes of these libraries. By leveraging promises, you can effectively manage data retrieval, maintain state, and ensure your applications remain responsive to user interactions, all while encapsulating the complexities of asynchronous programming. As developers, adapting to asynchronous programming and fully leveraging the future and promise pattern is no longer optional, but a necessity in today's software landscape. This pattern equips you with powerful tools to create fluid and efficient applications that not only meet user expectations, but exceed them. In summary, the future and promise pattern transforms how we handle asynchronous operations. It allows us to construct cleaner, more maintainable code while ensuring that our applications remain responsive and efficient. Remember the states of a promise: pending, fulfilled, and rejected, and leverage chaining and error handling to create robust asynchronous solutions. Reactive programming provides a powerful paradigm for managing and responding to changes in data. At the heart of this concept is the observer pattern, which effectively allows objects to observe changes in other objects. This means they can react dynamically when a change occurs. In today's lesson, we will dive deep into reactive programming using observables, focusing on how they can streamline event-driven programming and make your applications more responsive. So far, we learned about the future and promise pattern in asynchronous programming, enhancing application responsiveness and user experience. We explored how promises represent the completion or failure of asynchronous operations, simplifying error handling and supporting chaining multiple tasks. Additionally, we discussed the benefits of using Asyncio gather for executing concurrent tasks, making our code more efficient. Lastly, we recognized the importance of promises in modern web applications, emphasizing the necessity of mastering asynchronous programming for developers today. Now, we will cover observables in depth and see how they elevate reactive programming. In this example, we implement a basic observable using the RxPy library that emits a sequence of integers. We begin by importing the necessary modules, ensuring we have access to the reactive extension's functionalities. The creation of the observable is done through the from function, which takes a list of integers as the source of emitted values. Next, we subscribe to this observable using the subscribe method. This method allows us to define how we want to handle emitted values through callbacks. In this case, we provide 3 functions, one for processing received data, another for managing errors, and a final one that acts when the observable completes its emission. The onNext callback is crucial as it defines the action taken for each emitted value, printing it to the console. Similarly, the onError callback captures any potential errors during the stream and prints an error message, while onCompleted signals when the observable has finished emitting its values, giving us a clear and well-structured output. This demonstrates the fundamental mechanics of observables in managing data streams effectively. In this section, we will explore how to use the pipe method in conjunction with operators to transform values emitted by an observable. First, we create an observable using from that emits a sequence of integers from 1 to 5. This observable serves as our data source, which will provide values that can be manipulated. By applying the pipe method, we can introduce operators into our observable chain, enhancing its functionality. Here, we utilize the map operator, which allows us to apply a transformation to each emitted item. In this case, we multiply each number by 10. When we subsequently subscribe to the observable, we define the behavior for receiving the transformed values through the onNext callback. As the observable emits values, each one is processed by the map function before being sent to the observer. The output will now reflect these transformations, displaying the updated values of 10, 20, and 30 instead of the original set. This demonstrates the power of observables in modifying data streams dynamically, showcasing their role in reactive programming. In this section, we explore how to handle errors gracefully in a reactive stream using the catch operator. The code begins with the definition of a function called raiseError, which simulates an error by raising a value error. Following this, we create an observable that emits a sequence of numbers, specifically 1, 2, and 3, and then concatenates it with the result of calling raiseError. This effectively generates an observable that raises an error after emitting the initial numbers. To manage this error scenario, the catch operator is employed, allowing us to specify a fallback action when an error occurs. In this case, the fallback observable produces a recovery message that includes the error description. This ensures that rather than terminating the stream abruptly when the error occurs, the observable instead continues to function, providing a smooth user experience. Finally, the subscribe method is used to handle the emitted values, any errors, and completion notifications, demonstrating how to robustly manage errors in reactive programming while maintaining the fluidity of the data stream. In this section, we demonstrate how to create an observable that simulates a user input stream, allowing us to respond to user actions in real time. The useInputStream function acts as a generator, emitting values at 1-second intervals to mimic user input. Each time it emits an input, it invokes the onNext method of the observer, effectively sending the current user input to any subscribers. The observable is created using create, wrapping our user input logic in a way that makes it easy to subscribe to. By calling the subscribe method on the observable, we attach 3 callbacks. The onNext callback processes emitted values, the onError callback handles any potential errors, and the onCompleted callback signifies the end of the input stream. As the program runs, subscribers receive immediate feedback with the printed messages corresponding to the user input, illustrating the responsiveness and interactivity that observables can bring to applications requiring real-time updates. This example highlights the flexibility and power of observable streams in enhancing user experiences. In this section, we will explore how to combine multiple observables using the combine latest operator in RxPy, unveiling a practical approach to synchronize data streams. The code begins by simulating two observable data streams with obs1 and obs2, where obs1 emits values every second, and obs2 does so every 1.5 seconds, generating random integers. With the combine latest operator, we create a new observable named combined. This operator emits a pair of the most recent values from both obs1 and obs2 whenever either stream produces a new value. The result is a coherent synthesis of both data streams that allows for a comprehensive view of the data landscape. We subscribe to the combined observable with callbacks for processing emitted values, handling errors, and signaling completion. When the subscription is active, it prints the combined output to the console. To keep the program running and allow observation of the output for a span of 10 seconds, we utilize a sleep function. This demonstrates how easily RxPy enables developers to handle real-time data, allowing applications to respond effectively to simultaneous inputs from multiple sources. In this segment, we introduce the concept of schedulers in RxPy, which play a crucial role in managing the execution context of our observables. The code demonstrates an observable emitting a sequence of numbers while utilizing the new thread scheduler. This scheduler allows the emissions to be processed in a separate thread, thereby freeing up the main thread for other tasks, such as maintaining a responsive user interface. The observable is created from a list of integers, and upon subscription, the subscribeOn method is employed to specify that emissions should occur on a new thread. Inside the subscribe method, we define callbacks to handle the emitted values, errors, and completion of the observable. The onNext callback prints each received value, indicating it is being processed on the new thread. After processing all values, a completion callback confirms the end of emissions. To maintain the main thread's activity, a short sleep is incorporated before the program exits. This example effectively illustrates how using schedulers can enhance application responsiveness, allowing developers to manage complex data streams without compromising the user experience. In conclusion, observing reactive programming through the lens of observables brings a wealth of benefits to developers. From creating responsive user interfaces to smoothly managing real-time data, observables empower your applications to react dynamically to whatever data streams present themselves. By understanding the observer pattern and effectively utilizing tools like RxPy, we've explored how observables can enhance the architecture of your applications and reduce complexity when dealing with asynchronous data. The key takeaways include the ability to create observables, transform data with operators, handle errors gracefully, respond to real-time user inputs, combine multiple data streams, and effectively manage threading with schedulers. These foundational concepts make it easier for developers to build robust, scalable applications without getting bogged down in complex callback structures. As we continue to explore advanced reactive programming topics in future lessons, we'll unpack more powerful techniques and libraries, enabling you to take your applications to the next level. Thank you for joining this exploration of observables today, and I look forward to seeing you in our next session. Happy coding! In the world of software development, performance is key. Today, we're diving into the concept of performance patterns, which offer essential strategies to optimize system efficiency and responsiveness. Whether you're building a high-traffic application or a simple utility, understanding these patterns will help you write code that not only works well, but also performs beautifully. So far, we learned about reactive programming and its core concept of observables, which allow for dynamic data handling and enhance application responsiveness. We explored the observer pattern, the benefits of using the RxPy library for managing observables, and how they can transform, handle errors, and respond to real-time events. Additionally, we discussed combining multiple observables and utilizing schedulers to ensure seamless execution in applications. These insights lay the groundwork for building robust, scalable applications with advanced reactive programming techniques. Now, we will cover performance patterns and how they can elevate your software to the next level. In this example of the producer-consumer pattern, we demonstrate how two threads can operate concurrently without interfering with each other. The code begins by importing necessary modules: threading, time, and queue. The producer function generates 5 items, placing each into a queue with a 1-second delay to simulate processing time. It prints a message indicating each item produced, allowing us to track its operation. On the other hand, the consumer function continually retrieves items from the queue until it encounters a sentinel value, none, which signals it to stop. Each time an item is consumed, a message is printed, and there's a longer, 2-second delay to simulate the time taken for processing each item. This setup effectively illustrates decoupling. While the consumer may take longer to process items, the producer continues generating new items without waiting for the consumer to catch up. The use of threading ensures that both the producer and consumer can function simultaneously in their own threads, maximizing throughput and preventing potential application lag or crashes. By employing the queue to manage task distribution, we can efficiently handle workloads in concurrent programming environments. In the following code, we implement a basic caching pattern using a dictionary to store the results of a computationally expensive function, which can significantly enhance efficiency. The cache dictionary serves as temporary storage, allowing us to avoid redundant calculations. When the expensive function is called with a specific argument, the function first checks if the result is already present in the cache. If it is, it retrieves the value from the cache, providing immediate access and saving time. If the argument isn't found in the cache, the function proceeds to perform the expensive computation, simulating this delay with a sleep function to represent lengthy calculations. Once computed, the result is stored in the cache, ensuring that future calls with the same argument will benefit from this cached value. This approach not only reduces processing time, but also optimizes resource usage, emphasizing the importance of caching in application development. Ultimately, such a pattern can greatly improve performance, especially in scenarios involving multiple, repeated requests for the same data. In this example, we implement the bulkhead pattern using Python's concurrent futures module, which allows us to manage concurrent service calls while ensuring that the overall system remains resilient. The service call function simulates a delay for each service request, representing varying response times with a random sleep duration between 0.1 to 1.5 seconds. This models real-world situations where external services may respond slowly or fail. The bulkhead pattern function sets up a thread pool with a maximum of 3 concurrent workers, allowing us to manage multiple service calls without overwhelming the system. Using a dictionary comprehension, we submit 5 service calls to the executor and keep track of their futures, the results of the asynchronously run tasks. As each service call completes, we utilize concurrent futures as completed to handle their results as they finish. This approach enables us to print the success messages of completed service calls while also catching and reporting any exceptions that may arise, thus demonstrating how the bulkhead pattern effectively isolates failures and prevents them from impacting the overall system performance. By limiting concurrent execution and ensuring loose coupling, we enhance system reliability and throughput. In this section, we will delve into the implementation of the circuit breaker pattern, a vital mechanism in distributed systems designed to prevent cascading failures. We begin by defining a circuit breaker class that encapsulates the logic for monitoring service calls. The constructor initializes essential parameters, including a failure threshold that indicates how many failed attempts will trigger the circuit breaker to open, and a recovery timeout that specifies how long it must wait before resetting. Within the class, the call service method is responsible for managing the service calls. It checks the state of the circuit. If it's open, it verifies whether enough time has passed since the last failure before transitioning back to closed. If the service call is successful, the failure count resets, whereas an exception increments the count. Significantly, if the failure count meets or exceeds the threshold, the circuit breaker shifts to the open state to block further service attempts, allowing time for recovery. We illustrate its functionality using a mock unreliable service that simulates failures. By repeatedly invoking the call service method, we can observe how the circuit breaker manages service calls effectively, thus enhancing system resilience during failures. In this section, we implement the queue pattern, which is crucial for managing high loads efficiently. The code begins by importing necessary modules: queue for thread-safe handling of items, threading for concurrent processing, and time to simulate delays. We define a worker function that continuously retrieves items from the queue. If it encounters a sentinel value, none, the loop breaks, signaling that there are no more items to process. Inside the loop, it processes the item while printing a message and simulating a time-consuming task with a sleep function, followed by marking the task as done with queue task done. Next, we initialize a queue and start a worker thread, setting it as a daemon so that it runs in the background. In the main section, we produce items in a loop, adding them to the queue while printing a production message. This decouples the production from consumption, allowing the application to handle multiple tasks without blocking. Finally, we wait for all tasks to finish with queue join, ensuring that all items are processed before the program concludes. This demonstrates how the queue pattern facilitates efficient task management in applications. As we wrap up, we've explored a selection of performance patterns that empower developers to write more efficient, scalable applications. These patterns, including the producer-consumer, caching, bulkhead, circuit breaker, and queue patterns, serve as invaluable tools in your software development toolkit. By implementing these patterns, you'll enhance your application's resilience and responsiveness, ultimately leading to better user experiences. Embrace these strategies as you continue to develop your skills in building performant applications. Remember that understanding and applying these concepts will yield both immediate benefits and long-term improvements in your software development journey. Happy coding! In this implementation of the cache-aside pattern, we define a book cache class to manage book data efficiently. The constructor initializes an empty cache represented by a dictionary, allowing for quick data retrieval. When a user requests a book through the getBook method, the system first checks if the book ID exists in the cache. If the book is found, it retrieves the information directly from the cache, which is faster and saves time. If the book isn't available in the cache, the method simulates fetching the book data from a database, emphasizing the importance of minimizing expensive operations. Once the data is retrieved, it stores the book in the cache for future requests, thus improving response times for subsequent fetches. The application notably showcases performance optimization by reducing redundant calls to the slower database and highlights efficient resource usage. Finally, two example calls demonstrate this functionality. The first call retrieves the book from the database, while the second call fetches it directly from the cache, illustrating the time-saving benefits of this pattern. In the following code, we implement Memoization to optimize the calculation of Fibonacci numbers, a classic example of a problem where overlapping subproblems can lead to inefficiency. The Memoza class encapsulates a dictionary named Memo, which stores previously computed Fibonacci values. When invoking the fib method of the Memoza class, the function first checks if the Fibonacci number for the input n already exists in the memo dictionary. If it does, the method retrieves the value from the cache, saving the time that would have been spent recalculating it. If the value is not present in the cache, the function prints a message indicating that the calculation is taking place, and then computes the Fibonacci value using recursive calls to fib_n1 and fib_n2. The computed value is stored in the memo dictionary before returning it. Finally, in the example loop at the bottom, we call Memoiza, fib I for numbers from 0 to 9, demonstrating how memoization significantly enhances performance by avoiding redundant calculations. This approach to caching function results is especially powerful for problems that involve recursive computations. In this section, we implement the lazy loading design pattern using the lazy image class, which illustrates how to defer image loading until it is absolutely necessary. The class is initialized with the path to an image, and the actual image data is stored in a private variable image, which starts off as none. The crucial part of this class is the load method. When this method is called, it first checks if the image data has already been loaded by verifying if image is none. If it is, the class simulates loading the image from disk and stores the loaded image in image. This effectively prevents unnecessary resource consumption by avoiding immediate loading of all images, which can be particularly beneficial in applications like image galleries where initial page load times can be a concern. Moreover, on subsequent calls to the load method, as the image is already loaded, it simply returns the cached data without needing to load it again. This approach significantly enhances user experience by reducing initial load times and optimizing resource utilization on web applications. Let's summarize what we covered. We explored the cache-aside pattern, where your app checks a cache for data first before hitting the slower data sources. We also discussed memoization, which enhances performance by storing previously computed values, especially useful in recursive functions. To wrap it up, we examined lazy loading, which delays the loading of resources until they are actually needed, thereby optimizing performance in applications significantly. By integrating these strategies into your application architecture, you can not only enhance the user experience by reducing load times, but also improve the overall efficiency of your applications. Keep practicing these patterns, and you'll see just how much smoother your applications can run. Happy coding! In the realm of software engineering, understanding design patterns is like mastering the building blocks of effective applications. Patterns are tried-and-true solutions to common problems, enabling developers to enhance the efficiency and scalability of applications. So far, we learned about several powerful techniques for enhancing application performance, including the cache-aside pattern, memoization, and lazy loading. The cache-aside pattern allows applications to check a cache for data before accessing slower backing stores, while memoization optimizes recursive function calls by caching results. Lazy loading defers the initialization of objects until needed, improving resource efficiency and reducing load times. By incorporating these methods, developers can significantly enhance application responsiveness and efficiency. Now we will cover some key design patterns beyond those, focusing on how they can transform your development processes and ultimately your application's performance. The provided code demonstrates the implementation of the singleton pattern in Python, a design pattern that guarantees a class has only one instance while providing a global access point to that instance. At the core of this implementation is the singleton class, which contains a class variable instance that is initialized to none. The magic method new is overridden to control the instantiation process. When a new object of singleton is created, the method checks whether instance already holds an instance. If it does not, it invokes the superclass's new method to create a new object and assigns it to instance. If instance already exists, the method simply returns this existing instance. The example usage of the class illustrates how creating two instances, singleton1 and singleton2, results in both variables pointing to the same object. This is confirmed by the print statement, which outputs true. This aspect is crucial for scenarios that require centralized control, such as ensuring a single instance of a logging utility or a configuration manager within an application. In our implementation of the observer pattern, we first define a subject class that manages a list of observers interested in its state changes. This class has an attach method, allowing observers to register themselves so they can receive updates when the subject is notified. The notify method is crucial. It iterates through the list of observers and calls the update method, passing along any new data. Next, we create an observer class with an update method that specifies how the observer should respond to notifications. In our example usage, we instantiate a subject and 2 observer objects. After attaching both observers to the subject, calling the notify method on the subject with new data triggers the update method on each observer, demonstrating how they respond to changes in the subject's state. This pattern exemplifies the power of decoupling. The subject doesn't need to know the details of its observers, promoting flexibility in adding or removing observers and ensuring that all components in the application stay synchronized effortlessly. In this section, we delve into the factory pattern, which simplifies object creation by abstracting the instantiation process. The character class serves as a base class with an attack method that is not implemented, essentially laying the groundwork for specific character types. The warrior and mage classes inherit from character and provide their unique implementations of the attack method, showcasing polymorphism. At the heart of this pattern is the character factory, which contains a static method, createCharacter. This method takes a string specifying the character type and returns an instance of the corresponding character class, either warrior or mage. This delegation of responsibility allows the client code to create character objects without needing to know the details of the instantiation process. If an invalid character type is provided, the factory raises an exception, ensuring that only valid objects are created. This encapsulation not only promotes cleaner and more maintainable code, but also enhances flexibility, as new character types can be easily introduced without modifying existing code. The code showcases an implementation of the strategy pattern, which allows for dynamic algorithm selection at runtime. At the heart of this design is the sort strategy class, serving as an abstract base class that defines a common interface for all sorting strategies. By inheriting from this class, both the quicksort and bubblesort classes implement their own versions of the sort method. The quicksort class provides a placeholder for quicksort logic, allowing for the use of Python's built-in sorting for demonstration purposes, while bubblesort manually iterates over the data to swap adjacent elements until the list is sorted. The sorter class acts as a context that maintains a reference to a sort strategy instance. It offers the ability to set or change the sorting strategy dynamically through the setStrategy method, thus enabling flexibility in choosing sorting algorithms without modifying the client code. In the example usage, the sorter begins with quicksort, demonstrating how easily the algorithm can be swapped to bubblesort, showcasing the primary advantage of the strategy pattern, the ability to introduce and manage various algorithms seamlessly. This structure ensures that the code remains clean and maintainable while permitting future extensions with new sorting strategies. In this section, we'll break down the implementation of the composite pattern, which allows clients to work with individual objects and compositions uniformly. The component class serves as an abstract base class for both individual components and composites, defining the common interface through the operation method. The leaf class extends component and represents the individual objects in our structure. When its operation method is called, it simply returns a string indicating that it is a leaf. The composite class, also derived from component, manages a collection of leaf objects. It contains an add method to facilitate the addition of these children components. The real strength of the composite pattern shines in the overridden operation method, which iterates through its children, invoking their operation methods and aggregating the results. This enables the composite to represent the entire structure, demonstrating a uniform way of treating individual and composite components. With an example usage provided, we can see how the composite object can hold multiple leaf instances, allowing for flexible and scalable representation of tree-like structures in applications. To sum up, we have covered several design patterns that are indispensable in software development. The singleton pattern helps with single-instance management, the observer pattern enables real-time updates, the factory pattern streamlines object creation, the strategy pattern allows interchangeable algorithms, and the composite pattern organizes hierarchical structures. By understanding and applying these design patterns, you can create applications that are not only efficient and scalable, but also easy to maintain and extend. As you progress in your software engineering journey, leveraging these patterns will transform the way you approach problem solving. Incorporate them into your toolbox and watch as they elevate your coding skills, enhance application performance, and lead to more successful project outcomes. Happy coding! Throttling is an important pattern we may need to use in today's applications and APIs. The principle behind throttling is to regulate the flow of data or requests to ensure that resources remain available and performance is optimized. In our increasingly digital world, where applications can receive an overwhelming number of requests in a short period, implementing a throttling pattern is essential for maintaining performance and user experience. So far, we learned about key design patterns in software engineering, including the singleton, observer, factory, strategy, and composite patterns. Each of these design patterns serves a unique purpose in software development. Having established that foundation, now we will talk about the throttling pattern, how it works, its use cases, and how we can implement it effectively. To understand throttling better, let's break down its main purpose. Throttling allows applications to control the rate at which requests are processed. Imagine a scenario where a website experiences a sudden spike in traffic, for instance, during a major online sale. If the application isn't throttled, it could struggle to handle all incoming requests, potentially leading to crashes or degraded performance. Therefore, implementing throttling ensures we can maintain a smooth user experience even during peak times. In this section, we delve into the implementation of a basic rate limiter using Python, which is a fundamental approach for controlling request rates in applications. The rate limiter class is designed to manage the number of requests allowed within a specified time frame. It accepts two parameters: max requests, which sets the ceiling on the number of requests, and time window, which defines the duration within which those requests are counted. Internally, the class utilizes a deck to efficiently store timestamps of the requests. This data structure allows for quick removal of outdated timestamps that fall outside the permissible time window. The core functionality hinges on the alloRequest method, which first clears out any old requests from the deck, and then checks if the current request can be permitted based on the defined limits. If the limit has not yet been reached, the request timestamp is added to the deck, and the method returns true, indicating the request is allowed. Otherwise, it denies the request. This mechanism ensures that the application manages traffic while maintaining responsiveness, reflecting the importance of throttling in software design. The throttling mechanism created above is a useful safeguard against overwhelming web services. However, there are a few variations of throttling worth mentioning. One of them is the token bucket algorithm. Here, tokens are added to a bucket at a constant rate, and each request requires a token for processing. If the bucket is empty, requests are denied until tokens are available again. In this implementation of the token bucket algorithm, we create a class called tokenBucket that manages requests based on the number of available tokens. Upon initialization, we set the maximum number of tokens the bucket can hold, capacity, and the rate at which tokens are added, fill rate. The add tokens method allows us to replenish the tokens based on the elapsed time since the last check, ensuring that the total does not exceed the defined capacity. The alloRequest method is responsible for handling incoming requests. It first invokes add tokens to update the token count before checking if any tokens are available. If there are tokens left, it decrements the token count by 1 and permits the request, returning a Boolean value indicating the request status. On the other hand, if there are no tokens available, the method denies the request. With this design, the token bucket can effectively accommodate burst requests while adhering to a specified limit, enhancing user experience during traffic spikes. The provided example usage illustrates how the bucket can be instantiated and tested over a series of simulated requests, demonstrating its behavior in granting or denying access based on token availability. While using throttling patterns, we must also consider scenarios like API rate limits when integrating with external services. Many APIs enforce strict rate limits to prevent abuse and ensure fair usage among clients. Therefore, it's critical to accommodate these limits in your application design. In this section, we will explore how the API rate limiter class effectively manages the rate of outgoing API requests to comply with external service limits. The class is initialized with parameters that define the maximum number of requests allowed in a specified time frame, using the previously defined rate limiter class to enforce these constraints. The request method is key to this implementation. It enters a loop that continually checks whether a request is permissible by calling the alloRequest method from the rate limiter. Should the limit be reached, the program will pause execution, outputting a message to inform the user that the rate limit has been exceeded and it is waiting. This pause prevents excessive requests to the external service, respecting its constraints and preserving the application's integrity. When the request can proceed, a GET request is made to the specified URL using the requests library, and the JSON response is returned. An example provided demonstrates how the API rate limiter can limit 3 requests every 5 seconds while iterating through 10 attempts, effectively illustrating how the throttling mechanism safeguards against potential overloads while interacting with external APIs. There are various use cases for throttling, particularly in large-scale applications, such as load balancing across servers, API rate limiting, and managing resources in cloud computing environments. By implementing throttling patterns, developers can ensure their applications remain responsive and efficient. An exciting aspect of throttling is that it also aligns with the principles of resilience in software engineering. By protecting your system against overload, you're creating a more robust infrastructure that can handle unexpected spikes or failures gracefully. As we dive deeper, it's pertinent to address the importance of monitoring and logging in connection with throttling. These practices allow you to analyze request patterns, identify bottlenecks, and adjust your throttling mechanisms as needed. Imagine running a busy e-commerce site during a major sale. Without visibility into how throttling impacts traffic and performance, you could miss crucial opportunities for optimization. Monitoring can be achieved using various tools and frameworks, such as Prometheus for metrics collection, combined with Grafana for visualization. Implementing this monitoring would help you assess whether your throttling strategy effectively protects system resources or if adjustments are necessary based on real-time data. To summarize, throttling patterns are crucial for managing request rates and protecting applications from overloads. Through various strategies, such as the basic rate limiting and tokens bucket algorithms, developers can implement effective solutions tailored to their application's needs. Furthermore, coupling these strategies with monitoring practices fosters resilient and efficient software systems capable of handling real-world demands. In our journey of software design patterns, we've learned how essential throttling is in today's interconnected applications, enabling them to remain responsive, scalable, and user-friendly. Remember, Understanding the flow of traffic and system capabilities will serve you well, leading to well-architected systems that are prepared for anything. Thank you for joining me today as we explored the throttling pattern. I hope you feel more equipped to tackle such challenges in your own projects. Retrying is an approach that is increasingly needed in the context of distributed systems. In our digital world, network requests can fail for a myriad of reasons, including timeouts, congestion, or transient faults. When these issues arise, having a retry mechanism in place can be critical for maintaining application stability and enhancing user experience. So far, we learned about the significance of throttling in modern applications and APIs, emphasizing its role in regulating data flow and maintaining performance during high traffic. We examined key concepts, including the implementation of a basic rate limiter and the token bucket algorithm, to manage request processing effectively. Additionally, we discussed the importance of integrating throttling with external API rate limits and monitoring practices to optimize system response and resilience. Ultimately, these techniques are vital for ensuring user-friendly, scalable, and robust software systems. Now, we will talk about the retry pattern, exploring how to implement it effectively in distributed systems. The retry pattern aims to automatically retry an operation, often when it fails due to transient issues. This is essential in distributed environments where components communicate over a network, and the likelihood of failures is inherently higher. For instance, if a request to an external service fails, rather than immediately terminating the transaction, we can leverage the retry pattern to give it another shot. One fundamental understanding we need to grasp is that not all errors are equal. It's important to differentiate between transient errors that may resolve themselves on the subsequent attempt and permanent errors that signify a failure that won't be fixed by simply retrying. Permanent errors might include issues like an invalid request, while transient errors could involve network congestion or service unavailability. The solution is often to implement an exponential backoff strategy, a method where the wait time between retries increases exponentially. In this section, we focus on implementing a retry mechanism in Python with an exponential backoff strategy. The perform network request function simulates a network request that fails 70% of the time, raising an exception to indicate a failure. This randomness mimics real-world scenarios where network calls can often fail due to various issues. The core of this implementation is the retry request function, which attempts to call perform network request multiple times, up to a defined number of attempts specified by max attempts. If a request fails, the code captures the exception, prints an error message, and calculates a delay before retrying. With each failed attempt, the delay increases exponentially, starting from base delay and doubling with every retry, making it less likely to overwhelm the failing service. This method allows the system to give the external service time to recover. Finally, if all attempts fail, a message indicates that the retry process has exhausted all possibilities. This structured approach not only systematically manages errors, but also helps improve application stability in the face of transient failures. In this section, we enhance our retry mechanism by incorporating logging to better understand the outcome of each attempt. The code begins by configuring the logging library to display info-level messages, which provides insights into the success and failure of our requests. The retry request with logging function is designed to attempt network requests multiple times, which is particularly useful in distributed systems where failures can occur. For each attempt, the function tries to perform a network request. If successful, it logs the result, including the attempt number and the outcome, allowing developers to see which attempts succeeded. Should the attempt fail, a warning is logged detailing the specific exception encountered, making it easier to debug issues later. If there are remaining attempts, the code calculates an exponential backoff delay before retrying, signaling the pause duration in the logs. Finally, if all attempts fail, a critical error is logged, indicating the failure of the entire operation. This approach not only improves error handling through retries, but also provides a clear trail of events that can inform adjustments in the retry strategy over time. In this section, we implement a retry mechanism that intelligently distinguishes between transient and permanent errors. The code defines two custom exceptions: transient error, which is used for temporary issues that may resolve themselves, and permanent error, which indicates a failure that cannot be resolved by retrying. The function perform network request v2 simulates a network operation that has a 70% chance of failure. Depending on a further random check, it raises either a transient error or a permanent error. This setup allows our retry logic to respond appropriately based on the type of failure encountered during the network request. The core of the retry logic is encapsulated in the retry request with error handling function, which attempts to call the perform network request v2 function. Upon catching a transient error, it retries the request with an exponential backoff delay, increasing progressively with each attempt. Conversely, if a permanent error is raised, the function stops retrying immediately. This structured approach to error handling empowers developers to create robust systems that handle network issues gracefully and efficiently, optimizing application resilience in distributed environments. In this section, we focus on implementing a rate-limited request function to effectively manage how often requests are sent to an external service. The rate-limited request function takes two parameters: max requests and interval. This function allows us to control the maximum number of requests we send within a specified time period, thereby preventing overwhelming the service. Inside the function, we use a loop to attempt sending requests up to the defined maximum. For each attempt, we utilize a separate function, retry request with logging, which incorporates our previously defined retry mechanism, ensuring that if a request fails, it will automatically attempt to retry based on the defined logic. After each attempt, the code introduces a deliberate pause using the sleep function, allowing a specified interval to elapse before initiating the next request. This pacing is crucial in a scenario where multiple requests are being sent, as it helps mitigate stress on the external service, especially in distributed applications where multiple components interact. By combining retry logic with rate limiting, we enable more graceful handling of network issues while maintaining system stability and responsiveness. In this segment, we focus on implementing a timeout policy within our retry mechanism to enhance application responsiveness. The retry with timeout function begins by recording the start time, which serves as a reference for tracking how long the function has been executing. The main loop attempts to perform the network request based on the specified max attempts. Before each attempt, it checks whether the total elapsed time has exceeded the total timeout threshold. If it has, the function prints a message indicating that the total timeout has been exceeded and aborts further retry attempts, which prevents clients from waiting indefinitely for a response. Within the try block, the function executes the perform network request. If the request is successful, it immediately returns the result. However, if an exception occurs, the error is caught and a message indicating the failure is printed. The function then delays further attempts using an exponential backoff strategy, which increases the delay time exponentially with each attempt. This structure not only accommodates for transient errors, but also ensures that the overall request does not exceed a predefined timeout, enhancing both user experience and system stability. Recapping what we've covered, we explored the retry pattern and how it's an important method for increasing resilience within distributed systems. We discussed the significance of distinguishing between transient and permanent errors, applying exponential backoff in retries, and introducing effective logging practices. Moreover, we implemented customized exceptions for better error handling, integrated rate limiting, and included timeout policies to ensure our applications operate smoothly even under adverse conditions. Understanding and applying the retry pattern can elevate your applications, giving them the robustness needed in face of challenges that arise in distributed architectures. Adopting this strategy can lead to significant improvements in reliability and user experience, ensuring your software remains responsive and resilient to errors. Thank you for joining me in this discussion on the retry pattern. With these tools and techniques in your arsenal, you're well equipped to tackle challenges in your software projects. The mock object pattern is a powerful tool for isolating components during testing by simulating their behavior. This technique allows developers to create objects that mimic the behavior of real objects in controlled ways, providing a means to test components without relying on the actual dependencies. Think of it as creating a stunt double for your code. While the stand-in doesn't have the full capabilities of the original object, it behaves similarly enough to help you test effectively without the risks or complexities associated with the actual object. So far, we learned about the retry pattern in distributed systems, emphasizing its role in handling transient errors through automatic retries. We discussed the importance of distinguishing between transient and permanent errors, implementing exponential backoff strategies, and the benefits of logging attempts. Additionally, we explored how to integrate rate limiting and timeout policies to manage service interactions effectively. These practices enhance the resilience and reliability of applications when facing network issues. Now we will delve into the mock object pattern, exploring its functionalities, advantages, and how it can be implemented in real-world software projects. The primary advantage of the mock object pattern is that it promotes isolation in unit testing, which is crucial for achieving reliable test outcomes. When testing a component or method that interacts with external dependencies, such as databases, web services, or systems that may not always be available, using mocks allows you to simulate those dependencies. This isolation not only speeds up the testing process, but also eliminates potential side effects that could arise from using real components. For instance, if a database is down or a web service is returning unexpected results, those factors could skew your test results when using actual interactions. In this section, we will explore the implementation of the user-database interface and the user-statistics class, which showcases how to work with mocks in a user-statistics calculation scenario. The user-database class serves as a blueprint for database interactions, defining a method getUserData that must be implemented by any subclass. By raising a not-implemented error, it enforces that any concrete database class will need to provide its own version of how user data is retrieved, ensuring a clear contract for future implementations. The user-statistics class is designed to utilize the user-database interface to calculate the average age of users. Upon initialization, it takes a database parameter, which is expected to be an instance of a class that adheres to the user-database interface. Within the calculateAverageAge method, the class iterates over a list of user IDs, fetching their data via the getUserData method. By summing the ages of the users and dividing by the number of users, it computes the desired average. This structure illustrates how we can focus on testing business logic in isolation, decoupling our code from real database dependencies. In this section, we look at the implementation of a mock database designed for testing the user-statistics class. The mock user-database class is initialized with a dictionary representing user data, which facilitates testing without relying on a real database connection. This class provides a method, getUserData, which retrieves user information based on a given user ID. If the ID is not found, it returns a default age of 0, allowing the test to handle cases where user data may be missing without throwing errors. To ensure the user-statistics class functions correctly, we define a test function called testCalculateAverageAge. In this function, we create a mock dataset with specific ages associated with user IDs. We instantiate the mock database with this data and then create the useStatistics object, passing in the mock database. By calling calculateAverageAge with a list of user IDs, we test whether the average age calculation yields the expected result. This test emphasizes the importance of isolating components during testing, allowing us to verify functionality without introducing dependencies on external data sources. In this section, we take a closer look at the logging mock user database, which enhances our mock database by adding logging functionality to track user data access. This class introduces a key feature, a list called calls, which keeps a record of user IDs that have been accessed. When the getUserData method is invoked, it appends the accessed user ID to the calls list before returning the corresponding user data or a default value if the user ID is not found. This tracking allows us to verify which user data has been requested during testing. The added method, verifyCalls, plays a crucial role in our assertions. It checks if a specific user ID was accessed by returning a Boolean value based on whether the ID exists in the calls list. This mechanism not only provides insights into the interactions with the mock database, but also reinforces the importance of ensuring that the proper methods are called, thus enhancing the reliability of our tests. This approach integrates seamlessly into our unit tests, paving the way for more sophisticated validation of component interactions in our testing strategy. In this section, we enhance our testing strategy by implementing a logging mechanism within our mock database. The logging mock user database class is created to simulate database interactions while also tracking which user IDs have been accessed during testing. This is achieved through a list that records every user ID whenever the getUserData method is called. The primary functionality revolves around retrieving user data from a predefined dataset and logging calls made to the getUserData method. This allows us to not only simulate the expected data retrieval, but also to verify interactions with the mock. The verifyCalls method assesses whether the specified user ID was requested during the test execution. We then integrate this logging behavior into our test function, testGetUserDataLogging, where we instantiate the mock database with sample user data. After invoking the method to calculate the average age, assertions are made to confirm that both user IDs have been correctly accessed. This approach not only enhances the robustness of our tests, but also ensures our code logic for data retrieval functions as intended, facilitating maintenance and future development. In this section, we introduce the failing mock user database, which serves as a crucial tool for testing error handling in applications that depend on external databases. This mock database class simulates a scenario where the database is unavailable by raising an exception whenever the getUserData method is called. This behavior allows developers to test how their application responds to failures gracefully without needing a real database connection. By incorporating the failing mock user database into tests, we can ensure that the application correctly identifies and handles database-related errors. This capability is essential as it helps prevent unforeseen crashes during production and enhances overall system resilience. In practical terms, when we call the calculateAverageAge method of our useStatistics class using this mock, we can verify that an appropriate exception is raised, confirming that our error handling mechanisms are working as expected. Utilizing such mocks not only streamlines the testing process, but also elevates the robustness of the software being developed. In this segment, we focus on handling scenarios where the database interaction may fail, ensuring our application remains robust under such conditions. The code defines a test function, test database failure handling, which utilizes a mock database designed to simulate failures, specifically the failing mock user database. Within the test, an instance of useStatistics is initialized with this failing mock database. The essence of the test revolves around asserting the application's response to a database outage. When calculateAverageAge is called with a list of user IDs, the expectation is that it should raise an exception due to the mock's defined behavior. Exception handling is implemented using a tryExcept block, which captures any exceptions raised during the age calculation. Finally, the test checks whether the exception message matches our expectation of database not available. This validation is crucial because it confirms that the application can gracefully handle unexpected database failures, thereby enhancing its reliability and ensuring that it responds correctly in adverse situations. The benefits of employing the mock object pattern are vast. It allows for faster tests, clearer isolation of functionality, and ultimately leads to more maintainable code. It shines in situations that involve unpredictable behaviors and external integrations, reducing the friction between development and testing processes. Furthermore, by leveraging mocking frameworks available in many programming languages, such as Mockito in Java, Mock in Net, or Unitist, Mock in Python, the implementation of mocks can be simplified. These frameworks provide built-in support for creating, configuring, and asserting mock behaviors, streamlining the test writing process. As we wrap up our discussion on the mock object pattern, it's important to highlight that, while mocks bring various advantages, they should be used judiciously. Over-relying on mocks may lead to tests that do not accurately reflect real-world scenarios. A balanced approach that combines unit tests with integration tests is essential for ensuring comprehensive coverage of the software's behavior. In conclusion, the mock object pattern is a game changer in the realm of software testing. By isolating components, simulating behaviors, and providing deterministic outcomes, it empowers developers to write robust tests that can navigate the complexities of modern applications. As you continue developing your projects, consider the scenarios that could benefit from mocking and leverage this pattern to enhance your testing strategy. With mock objects in your toolkit, you're not just testing, you're orchestrating a symphony of reliable and maintainable code. In this section, we'll see how the user-service class uses the notification service to handle user registrations. The notification service class is responsible for sending notifications, encapsulating the logic needed to display messages. Within user service, we instantiate the notification service directly in the constructor. This creates a strong coupling between user service and notification service, which can complicate testing and future changes in our application. When we register a user, the registerUser method first executes the logic for user registration and then calls the sendNotification method of the notification service instance to notify when the registration is successful. While this approach works, it limits flexibility. If we ever want to change how notifications are sent, we would have to modify the user service code directly, illustrating a drawback of tightly coupled classes. This tight coupling is precisely why we later introduced dependency injection. By allowing the service to take notification functionality as input, we achieve greater flexibility and ease in testing, which are core benefits of the dependency injection pattern. In this example, we demonstrate how to implement the dependency injection pattern in a straightforward yet effective manner using a user service that relies on a notification service. The user service class is designed to accept a notification service instance via its constructor, promoting loose coupling by separating the responsibilities of user registration and notification handling. This approach allows for greater flexibility in terms of swapping out the notification mechanism, such as using a mock service for testing purposes or implementing alternative notification methods with minimal alteration to the user service. When we create an instance of user service, we pass in a notification service object. This instance is stored as an attribute within user service, ensuring that it can be utilized when necessary, such as when a user is registered. The invocation of the sendNotification method illustrates how notifications are dispatched immediately after user registration, showcasing the flow of control from user interaction to notification delivery. This design enhances testability, as one can easily replace notification service with a mock version to verify that notifications are sent correctly without relying on external systems. In this part of our tutorial, we implement the dependency injection pattern using interfaces and concrete service classes for notifications. First, we introduce the iNotification service interface, which establishes a contract for any notification service that will be created. This interface declares an abstract method, sendNotification, which all concrete implementations must define. Next, we create two classes, Email Notification Service and SMS Notification Service, both of which implement the iNotification Service interface. Each class provides its own implementation of the sendNotification method, enabling specific messages to be sent via email or SMS with appropriate feedback. Within the main function, we instantiate both notification services and subsequently create two user service objects, one configured to use the email service and the other the SMS service. This aspect of the code showcases how easily we can switch out services without altering the user service class, highlighting the central advantage of dependency injection: flexibility. This allows developers to extend functionalities, like adding new notification methods, without needing to modify existing code. Ultimately, this design promotes a cleaner and more maintainable architecture. In this section, we illustrate how to effectively use a mock service to facilitate unit testing of the user service. We begin by creating a mock notification service class that implements the iNotification service interface. This mock service accumulates messages sent during testing in a list, allowing us to verify the proper functionality of user service without sending actual notifications. The sendNotification method appends the provided message to messages sent, simulating notification behavior. Next, we define a test function, testRegisterUser, which demonstrates how to utilize our mock service. Within this function, we instantiate mock notification service and pass it as a dependency to user service. We then proceed to invoke the registerUser method with a sample username, which triggers the notification mechanism. Finally, we assert that the expected notification message is present in the mock service's messages sent list, validating that the user service operates as intended. This approach underscores the ease of testing with dependency injection, allowing us to isolate user service from external dependencies while ensuring its correctness. In this code, we see an example of method injection within the user service class. The registerUser method takes both a user and a notification service as parameters, allowing for flexible dependency management. This design enables various implementations of notification service to be passed in each time registerUser is called, meaning that different types of notification services can be utilized without changing the call logic of the user service. While this approach provides significant flexibility, it also introduces some challenges, as it requires the caller to be aware of the specific dependencies needed during each method call. This can lead to cluttered method signatures, making it harder for developers to immediately grasp what dependencies the class relies on. Furthermore, constant vigilance is necessary to ensure that the right instances of the services are supplied, as failing to do so might result in runtime errors. Thus, although method injection can be powerful, it's important to weigh its benefits against potential drawbacks in managing complexity and clarity in your application's design. In this example, we are looking at property injection within a class that requires a notification service to function properly. The user service class is designed in such a way that it initializes with notification service, set to none. This means that after creating an instance of user service, the notification service property needs to be set explicitly before any operations can occur. When a user attempts to register through the registerUser method, the code checks if the notification service has been set. If it hasn't, an exception is raised, ensuring that the service is available to send notifications when a user is registered. This approach exemplifies the flexibility that property injection provides, as it allows the notification service to be set at any point post-instantiation. However, it also highlights a significant risk. Without careful management, it's possible for an instance of user service to be in an invalid state, leading to errors during execution if the property isn't set. Thus, while property injection can enhance flexibility, developers must ensure all dependencies are addressed before invoking methods in the class. Now, as we wrap up our exploration of dependency injection, it's essential to highlight some best practices. Firstly, always favor constructor injection where feasible, as it provides clarity and robustness. It ensures all dependencies are present from the moment the object is created, avoiding any unintended null references. Secondly, keep your dependencies minimal. The fewer dependencies a class has, the easier it is to manage and test. Additionally, think about encapsulating your dependencies in cohesive packages. The more focused your classes are on their core responsibilities, the more maintainable your code becomes. Lastly, leverage dependency injection containers when scaling up your applications. These frameworks automate the injection process and manage lifecycle concerns, making them incredibly useful for large applications. Libraries like Spring in Java or Netcar's built-in DI container allow for more complex scenarios, providing a robust infrastructure for managing dependencies as your application grows. In conclusion, the dependency injection pattern is a powerful design strategy that enhances flexibility, increases testability, and improves maintainability in software applications. By defining dependencies externally and injecting them into our classes, we allow for a cleaner architecture and a more agile development process. As you incorporate this pattern into your projects, you'll find that it promotes a more structured approach to dependency management that will ultimately yield better, more maintainable code. So, whether you're building a small utility or a large enterprise application, consider how dependency injection can fit into your architecture and enjoy the benefits of a design tailored for change and growth. Python is an incredible programming language known for its simplicity and versatility. However, even experienced developers can fall into certain traps, leading to what are known as anti-patterns. These practices might not inherently be wrong, but they often result in code that is less efficient, harder to read, and tougher to maintain. Today, we'll dive into some common Python anti-patterns, understand what they are, and discuss how we can avoid them to produce cleaner, more efficient code. So far, we've learned about dependency injection, enhancing flexibility, testability, and maintainability by externalizing dependencies. We've explored how it leads to cleaner and more modular code. Now, let's transition into discussing Python anti-patterns to ensure we refrain from coding practices that could hinder our progress. In this example, we see a class definition in Python, which introduces the concept of encapsulation and object-oriented programming. The class named myClass serves as a blueprint for creating objects, encapsulating related behavior and data. Within this class, we have two methods, method 1 and method 2. However, it's essential to note that these methods currently contain only the pass statement, indicating that they are placeholders for future implementation. Proper indentation is critical in Python, as it defines the structure and flow of the program. Each method is intended to be indented under the class definition, showcasing the relationship between the class and its methods. Following the PEP 8 style guide, each method is indented with 4 spaces, making the code not only functional, but also readable and maintainable. By adhering to such conventions, developers ensure that their code remains clear, allowing others to understand the logic and purpose behind the class and its functionalities. In this section, we focus on the organization of imports in Python, following PEP 8 guidelines for a clear and structured codebase. The initial example displays an incorrect import style, where multiple modules are imported on a single line without separation, which can make it difficult to read and understand the code's dependencies. By contrast, the corrected example illustrates the recommended format. Each standard library is imported on its own line, followed by an empty line before third-party libraries and local imports. This structure not only enhances readability, but also helps developers quickly identify the origin of each module. By adhering to these conventions, you create a cleaner code environment that promotes collaboration and eases navigation, as others can immediately see which modules are being used and their classifications. Such organization fosters a professional coding style, ultimately benefiting both the author and those who work with the code in the future. Now, let's examine the importance of naming conventions in Python through two contrasting examples of function, class, and variable naming. In the first instance, we see a function named calculateSum, which does not adhere to the recommended lowercase with underscores format. This naming choice can hinder readability, especially in larger projects where clarity is crucial. Similarly, the class name myClass uses lowercase letters instead of the prescribed capwords convention, making it inconsistent with Python standards. The variable maxValue also deviates from the expected all caps naming for constants, further complicating code comprehension. In contrast, the revised code showcases appropriate naming practices. The function is now called calculateSum, which enhances its clarity by following the lowercase convention. The class name myClass employs capwords, aligning with Python-style guidelines, improving its visibility. Lastly, maxValue adheres to the all-caps format, making its purpose as a constant clear. Adhering to these conventions not only promotes clarity, but also assists future maintainers in understanding the code's intent without delving into its logic. Thus, proper naming is essential for writing clean, maintainable Python code. In this section, we will discuss the implications of using wildcard imports in Python. Wildcard imports allow you to import all the names from a module into your current namespace, as seen with the from mymodule import asterisk statement. While this might seem convenient at first glance, relying on wildcard imports can lead to significant problems in your code, namely cluttering the namespace with many variables and functions, making it hard to track where a specific variable originated and increasing the risk of naming collisions. In contrast, utilizing explicit imports, like from mymodule import myfunction, promotes clarity and better code organization. By importing only what you need, you not only improve readability, but also reduce the likelihood of unintended bugs creeping into your program as your project scales. Explicit imports make it easier for developers to understand which components from a module are being used, thus enhancing maintainability and aiding collaboration amongst team members. Embracing this approach is essential for writing clean, efficient code. In Python, there are two common approaches to handling operations that may fail. Look before you leap, LBYL, and easier to ask for forgiveness than permission, EAFP. The first example demonstrated uses LBYL by checking if the file exists before attempting to open it. This method starts by verifying the presence of the file using OSPauth exists. If the condition is true, it opens the file and prints its contents. Although this ensures that no error occurs during file access, it introduces unnecessary complexity with additional checks, which can clutter the code. In contrast, the EAFP approach exemplified in the second code snippet adopts a more Pythonic lens. By trying to open the file directly within a try block, the code anticipates that an error may occur, thus utilizing exception handling to manage it gracefully. If the file is not found, the code catches the file not found error and provides a user-friendly message instead of breaking the program. This cleaner error handling makes the code less verbose and easier to read, demonstrating the elegance of embracing exceptions as part of standard operations in Python programming. In this section, we'll explore the implications of inheritance versus composition in Python, examining how each approach affects code maintainability and flexibility. The first code snippet demonstrates a deep inheritance hierarchy with a grandparent, parent, and child class structure. While inheritance is a fundamental concept in object-oriented programming that allows a class to inherit properties and behaviors from another class, this example illustrates a potential pitfall. Deep hierarchies can create tightly coupled classes that make code harder to manage and understand, leading to complexities that can obscure functionality and introduce bugs. In contrast, the second code snippet advocates for composition, wherein the child class holds a reference to a parent instance rather than directly inheriting from it. This method reduces tight coupling between classes and offers greater flexibility. By favoring composition, the design becomes more modular, enabling easier changes or extensions later on. This shift enhances code readability and maintainability, demonstrating a more efficient way to structure relationships between classes while keeping the system adaptable to future requirements. Encapsulating state within a class is a powerful way to manage data in Python effectively. In the example of the counter class, we see how it maintains a count attribute, which initializes to 0 when an instance is created. This encapsulation prevents external functions from inadvertently modifying the counter's state, as the count is accessed and modified only through designated methods. The class provides two primary methods, increment and reset. The increment method allows for a controlled way to increase the count, ensuring that any increment operation is handled consistently within the class, promoting clear and predictable behavior. Meanwhile, the reset method provides functionality to revert the count back to 0. This structured approach not only enhances readability, but also makes the code more testable and maintainable. By using a class to encapsulate the counting logic, we achieve modularity, allowing for easy modifications and extension in the future without risking the integrity of the data it manages. Thus, adopting such practices can greatly improve overall code quality in Python applications. In Python, when checking the type of an object, using the type function can be misleading due to its failure to accommodate subclassing. This approach tightly couples the code to specific class types, which can undermine the principles of polymorphism. Instead, the isInstance function should be utilized, as it checks for an object's membership in a class hierarchy, effectively supporting subclasses. For instance, when we use isInstance useList, it confirms whether the object is an instance of useList or any subclass of it. This flexibility enhances code reliability by allowing the implementation of functionality that works across various subclasses without needing to rewrite type checks for each additional class. Enforcing the use of isInstance signals a more adaptable approach, preventing bugs that arise from unexpected type mismatches and greatly enhancing the maintainability of code. By adopting this practice, developers can write clearer and more effective object-oriented programs that leverage the full potential of inheritance, thus improving code quality in the long run. One of the common pitfalls in Python programming arises from using mutable types as default function parameters. The first function, append to list, demonstrates this issue. It initializes a list as the default value for the mylist parameter. What occurs here is that any modifications to mylist, such as appending the string default, persist across multiple calls to the function. As a result, invoking this function repeatedly will lead to the same list accumulating multiple default strings, potentially causing confusion and unexpected behavior. To address this problem, the second function, betterAppendToList, implements a more robust approach. Instead of using a mutable type as a default parameter, it sets the default value to none. Inside the function, a new list is created only when mylist is not provided. This reassures that every call to the function starts with a fresh list, preventing the accumulation of unwanted entries from previous calls. By following this pattern, developers can enhance the reliability and clarity of their code, avoiding unintended side effects associated with mutable default arguments. Let's explore the concept of encapsulation in Python by examining how to properly manage access to class attributes. In the first example, we define a book class that initializes two attributes, title and author, with a leading underscore to indicate that they are intended for internal use. However, by publicly accessing these attributes directly, we risk exposure to unintended modifications that could break our code. The second example illustrates a more secure approach through the BetaBook class, which introduces a public method, getTitle, that safely retrieves the title attribute. By using getters, we preserve the integrity of the internal state of the class. This encapsulation practice not only protects against accidental interference, but also allows for potential future modifications to the underlying data structure without affecting external code. In summary, leveraging methods like getters enhances code maintainability and readability, aligning with the principles of object-oriented design, by keeping internal workings hidden from the outside world. One common performance anti-pattern in Python is string concatenation within loops. The first example illustrates the ineffective approach by initializing an empty string and repeatedly adding elements from a list using the plus operator. This method is not only inefficient, but also leads to the creation of multiple intermediate string objects, which can significantly slow down performance, especially with larger datasets. In contrast, the second example demonstrates a more effective method utilizing the join method. By calling join on an empty string and passing in the list of strings, Python creates a single string in one go, thereby reducing overhead and enhancing speed. This method effectively concatenates the elements while optimizing memory usage and processing time. Adopting this approach is crucial for writing performant code, particularly in scenarios where string manipulation is frequent, as it leads to cleaner implementations and better overall performance. In this snippet, we explore the use of Python's functools, LRU cache decorator, which serves as an efficient caching mechanism to optimize performance, especially for expensive function calls. When we apply the @LRU cache decorator to the expensive function, it enables the function to cache results of previous calls. This means that if the function is invoked again with the same arguments instead of recalculating the output, which could be time-consuming, the function will return the cached result immediately. This greatly reduces the computational load and enhances the speed of the program, particularly when dealing with functions involving heavy calculations or data processing. The max size parameter defines the number of results to be stored in the cache, ensuring that it has a limit to prevent excessive memory usage. By utilizing this built-in feature, we not only simplify the caching process, but also significantly boost our code's efficiency and responsiveness, leading to a smoother user experience. This practice exemplifies how leveraging Python's robust standard library can lead to cleaner and more effective programming solutions. In summary, understanding and addressing Python anti-patterns is crucial for producing high-quality code. By focusing on code style violations, maintainability concerns, correctness pitfalls, and performance issues, we can develop applications that are cleaner, more efficient, and easier to maintain. So remember throughout your coding journey, good code isn't just about making it functional, it's about making it functional, maintainable, and scalable. Happy coding, and until next time, keep your code Pythonic. Understanding and avoiding common Python anti-patterns is crucial for writing cleaner, more efficient, and maintainable code. In this video, we'll dive into best practices that will help you sidestep these pitfalls and enhance your coding skills. So far, we've learned about Python's simplicity and the importance of avoiding anti-patterns that lead to inefficient and hard-to-maintain code. We've discussed crucial concepts such as dependency injection and the significance of adhering to PEP 8 style guidelines for better readability. Additionally, we explored how to organize imports, follow proper naming conventions, and utilize effective practices like explicit imports and proper exception handling. Ultimately, understanding and addressing these anti-patterns helps us write cleaner, more efficient, and maintainable Python code. Now, we will cover specific best practices to avoid these anti-patterns and enhance your Python programming. In this section, we focus on a practical demonstration of the dry principle in programming through the use of functions. The calculate area function is defined to compute the area of rectangles, illustrating how we can encapsulate common logic to avoid redundancy in our code. By specifying the parameters, length, and width, this function can take on different values for various rectangles without the need to rewrite the area calculation. The beauty of this approach lies in its reusability. Once the function is defined, we can call it multiple times with different arguments. For instance, when we need to calculate the area of rectangle 1 and rectangle 2, we simply invoke calculate area with the respective dimensions. This not only enhances code maintainability, but also emphasizes that any changes to the area calculation need only be made in one place, ensuring that our codebase remains clear and concise. By adopting this style, we reduce the risk of introducing errors, contributing to cleaner and more efficient programming practices. Let's examine how to avoid unintentional side effects in our functions by writing cleaner and more predictable code. In the first example, we have a function called addItem that appends an item to a global list called globalList. While this approach works, it creates side effects by modifying an external variable, making the function's behavior less clear and harder to track, potentially leading to bugs in larger programs. In contrast, the improved version of addItem accepts not only an item, but also a list as parameters. Rather than modifying the original list, it creates a new list by combining the existing list with the added item, ensuring the original remains unchanged. This functional approach promotes purity in programming, where the same inputs will always yield the same outputs without hidden changes to external states. By adopting this technique, we enhance the function's predictability and testability, a key aspect of writing clean and maintainable code. In Python programming, effective error handling is crucial for creating robust applications. The divide function demonstrates how to deal with potential errors, such as attempting to divide by 0. It encapsulates the division operation within a try-except block, allowing the program to catch a zero division error and provide user-friendly feedback instead of crashing. This practice enhances the resilience of the program by gracefully managing common pitfalls. Furthermore, the introduction of a custom exception, negative value error, emphasizes the importance of defining specific error types for various scenarios. The calculate square root function illustrates this by checking if the input value is negative. If it is, the function raises a negative value error, informing the user that square roots cannot be computed for negative numbers. By leveraging custom exceptions, your code becomes clearer and easier to maintain, as it categorizes errors meaningfully, improving both debuggability and user experience. This structured approach to handling exceptions leads to cleaner, more maintainable code, aligning with best practices in Python programming. Now, let's focus on enhancing performance by avoiding unnecessary computations within loops. In the first code snippet, the length of my list is recalculated during each iteration of the loop. This is inefficient because the length of a list remains constant, and recalculating it repeatedly adds extra overhead. To optimize this, the second code snippet calculates the length of my list just once prior to the loop. By storing the length in a separate variable, we reduce the number of calculations required and improve the performance of the loop significantly. Additionally, this approach not only makes the code more efficient, but also enhances its readability. When a loop iterates over a predefined number of items, it signals to the reader that we know exactly how many times we need to execute the loop, making the code easier to understand. Such minor adjustments in coding practices can lead to substantial improvements in the efficiency and clarity of your Python programs. Always remember, optimizing performance by avoiding redundancy in calculations can save processing time, especially in larger datasets. Using list comprehensions and generator expressions can significantly improve the clarity and performance of our code. In the given example, we start with a list of numbers ranging from 1 to 5. The first line demonstrates a list comprehension, where we create a new list containing the squares of each number in the original list. This method is not only concise, but clearly expresses our intention to transform the input list into a list of squared values in a single line. In contrast, the second line introduces a generator expression, which achieves a similar outcome, but does so in a memory-efficient way. Instead of generating the entire list of squared numbers at once, the generator computes each square on the fly as required. This is particularly advantageous when dealing with large datasets, as it avoids storing all the resulting values in memory simultaneously. By adopting these techniques, we enhance code efficiency and readability, embodying a more Pythonic approach to programming. In Python, understanding the differences between mutable and immutable data types is crucial for writing predictable code. The first code snippet demonstrates a function that modifies a list directly by using the append method. When we pass a list as an argument and add an item to it, the original list also changes, which can lead to unintended consequences if the list is being used in multiple places. This emphasizes the importance of caution when working with mutable types like lists. On the other hand, the second snippet showcases a function designed to work with a tuple, which is an immutable data type. Instead of modifying the original tuple, the function creates a new one by concatenating the existing tuple with the additional item. This approach maintains the integrity of the original data, illustrating how opting for immutability can lead to clearer and more manageable code. By favoring immutable types when appropriate, we can minimize the risk of accidental state changes and foster more stable programming practices. Effective logging is essential for understanding and diagnosing issues in your applications. In the code provided, we start by importing the logging module, which is a built-in library that enables us to log messages at different severity levels. We configure the logging settings by calling logging, basic config, and setting the logging level to info. This means that only messages with a severity level of info and above will be recorded, allowing us to filter out less important log messages. The processData function is defined to take a parameter called data. Inside this function, we use logging info to log a message indicating that data processing has begun, along with the actual data being processed. This provides a clear context for anyone reviewing the logs later, without overwhelming them with excessive details. Maintaining a balance between informative logging and conciseness is critical, as it ensures that relevant information can be easily found during development and troubleshooting. Overall, this setup emphasizes the importance of logging as a best practice in developing maintainable and efficient Python applications. In this section, we focus on the importance of documenting functions in Python to enhance code clarity and maintainability. The multiply function is a straightforward example that showcases how effective documentation can significantly improve understanding for both current and future developers. This function takes two parameters, x and y, which can be either integers or floats, and returns their product. The docstring associated with the function serves as a vital tool, clearly outlining the function's purpose, detailing the expected types of its parameters, and describing the return type. This level of clarity ensures that anyone who reads the code can quickly grasp what the function does without needing to dive into its implementation. Good documentation practices are essential not just for personal reference, but also for fostering collaboration among teams. It sets a standard that promotes communication among developers, allowing for better teamwork and efficiency down the line. By clearly documenting your functions like this, you contribute to a coding environment that values maintainability and readability, making your codebase welcoming and accessible to others. To sum it all up, understanding and applying best practices to avoid anti-patterns is essential in Python programming. By embracing the dry principle, writing pure functions, using meaningful exceptions, optimizing performance with comprehensions and memory-aware coding, opting for immutability when appropriate, implementing effective logging, and documenting your code well, you'll significantly improve your coding clarity and maintainability. Follow these guidelines, and your Python code will transcend from basic to wonderfully well-crafted, promoting a more robust development workflow. Until next time, happy coding!